In this video, we're going to be taking a look at kinematics, and we're going to do a full overview of 6 main areas that cover terms, calculations, strategies, ideas in order for you to have a good foundational understanding of kinematics that will be really helpful for AP Physics 1, but also for any high school course or even introductory college courses as well. Okay, so let's get started. We're going to start off with taking a look at some different terms and ideas, some basic stuff about terminology and how to understand different words that are going to make a significant change in what you solve for and how to interpret graphs and other ideas later on. We're going to start off with constant motion. After that, we're going to take a look at some main concepts, calculations, and take a look at some motion graphs, and then take it a step up from there and take a look at acceleration. Same thing, concepts, calculations, and graphs. And embedded in that, we're going to take a look at some problem-solving strategies and how to isolate variables. And then the last portion, we're going to start taking a look at 2 different things. We're going to be taking a look at free fall motion, objects only affected by the influence of gravity, its main concepts and important values. And then our most complicated part of our kinematics overview is likely going to be our projectile motion, which we're going to talk about concepts, problem solving, how to set up everything, take a look at everything that's going on to develop a good problem solving approach to those different sorts of questions and different calculations. All right, so let's go ahead and get into the first topic, which is the terms scalar versus vector and ideas. So the first thing we're going to start off with is taking a look at something called a scalar and something called a vector. And we're taking a look at these 2 things. Each of the values we're going to be looking at throughout this overview is either going to be a scalar or a vector. So a scalar is anything that has just a magnitude, which basically just means how large the value is, which is basically just represented by a number in most cases, especially in physics. And then with a vector, it is something that has a magnitude and a direction. And the direction is going to be a big piece in it because the direction is going to often determine whether something is positive or negative. So these are things that are a little bit more descriptive that we're going to be using a little bit more often in physics, and they will have positive and negative signs, which will tell us the direction. So common scalars would be things such as time, speed, and distance. So these things are just purely a number value to tell you how much of something you have, the amount of time that's elapsed, how fast you're moving, and then the actual length that you've traveled. That's time, speed, and distance. All of these must be positive because they are scalar values. When you're taking a look at speed, speed is actually distance over time. And since you're taking 2 scalar values that are just positive number values of the total length you traveled, divided by the total time elapsed, the speed is just going to tell you how fast you're going. But it won't give you any descriptors about which direction you're facing. Now with time, it is going to be in seconds, speed is in meters per second, and then distance is in meters. So if you're not in one of those basic metric units, then you definitely want to do a little conversion to get there. For vectors, ones that we're going to commonly use would be ones like velocity, displacement, and acceleration. Okay, those ones are all more descriptive values, and those can all be positive or negative, which are just going to tell you a little something about its direction. So is it going to the right or is it going to the left? Is it going up or is it going down? Is it speeding up? Is it slowing down? And then the formula for velocity is displacement, which is shown as a delta x, the change in position over time. And then because displacement can be a positive or negative value, that means that velocity can also be a positive or negative value, which means it'll tell you which direction that the object is going. For these ones have some of the same units. Velocity is in meters per second. Displacement is similar to distance, which is in meters. Displacement is just telling you your final position. minus your initial position, which you would either call xi or x naught. But that change in position, depending on where you make your origin, could be positive or negative. And then acceleration is in meters per second squared. It's how many meters per second you're changing per second. All right, so those are going to be 6 terms that are going to be very, very common. You want to make sure you understand what each of those mean in order to solve questions accurately and effectively. All right, so now let's start at taking a look at constant motion. Now for constant motion or constant velocity, that basically means that you're traveling and along the way you have the same displacement per time or per second. So maybe if your constant velocity is 2 meters per second, that means you're traveling exactly 2 meters on the dot every second that you travel. And then with constant velocity, you're mainly just using one formula. So if you take a look at the standard AP Physics 1 formula sheet, it'll give you a formula that looks like this, and it says final position equals initial position x naught plus v naught, the initial velocity times time, plus 1/2 at squared. Okay, that's a little bit overcomplicated for constant motion. What you all really need is just a condensed version of that. So for something that's going at constant velocity, that means your acceleration is always 0, which means that you're not adding or subtracting any amount of velocity to the object or person per second. Your change is always 0, which means you could be going fast or slow as long as your velocity isn't changing. Now for acceleration is 0, we don't need this entire part because it's going to go down to 0. And if you subtract the final position minus the initial position, that just gives us delta x. So we'll say delta x equals, and then v naught means initial velocity, but if the velocity isn't changing, you could just basically say it's v for velocity. So delta x equals v times t, or oftentimes it's written as delta x over t equals v, and all of those things we just mentioned earlier, which are displacement, which could be positive or negative. We have our time, which is always positive, and then we have our velocity, which is in meters per second. Now, when you solve for stuff, you're basically getting 2 out of the 3 variables, and then you're solving for the third. And in this case, if all of the forces are balanced, then you are going at a constant velocity, which would either be 0 or some non-zero number. All right, now let's go ahead and take a look at the graphs for constant velocity. We have position versus time graphs. We have velocity versus time graphs, and we have acceleration versus time graphs. For the first one, position versus time, if you are not moving at all, that means you have a completely flat line. That completely flat line could be anywhere, because if you have a constant position over time, that means you're just standing there and you're at rest. Now, if you take the change in position per time, which is the slope, that slope tells you the velocity, because the velocity is the change in position per time. If you take a look at this slope, that is a 0 slope. That means you have 0 velocity because you're at rest anyways. So it's 0 right at that x-axis. And then for constant velocity, as I said earlier, that means all of your accelerations are 0. So we are for sure going to have no change in velocity, which means your acceleration is 0. And the change in velocity per time is acceleration. So again, moving down, you would take a look at the slope. So this has a 0 slope, which indicates that this one is 0. This one has a 0 slope that indicates that this one is 0. Now, there's not too many combinations for constant velocity. If you're moving forward at a constant velocity, you're going to have something that looks like this. And the steepness of that slope is going to tell you how fast you're going. So if it's more upright, so if it was slanted a little bit more upright like this, that tells you that the rate of its position changing per time is greater, which means it's going faster. Okay, I'm not going to add that on there though, because I don't want my graph to get too cluttered. But if it was a flatter or less steep slope, something that looked like this right under the green line, that means that its rate of change is less, which means that it's slower. Okay, now this one does have a constant positive slope, so it has a constant positive velocity. And then again, there's no slope here, so we're going to have no acceleration there. Okay, and then finally, if you're going backwards or just back towards the origin, then you're going to have a negative slope, something that looks like this. So if you're going backwards or towards the origin, you're going to have a negative slope, something that looks like this. And again, that steepness of the slope is going to tell you how fast you're going. So if it's more upright, that means you're moving faster. Now, since we have a constant negative slope, that means we have a constant negative velocity. And again, there is no slope there, so we have no acceleration. Okay, so for the acceleration versus time graphs, they are the worst descriptors of what's happening because all of them are going to be zero. Okay, when you're taking a look at the position versus time graphs, it's basically, are you not moving away from the origin, like the green one in the forward direction, or are you moving towards the origin or backwards, like the purple one? Since it's constant velocity, all of your lines on the velocity versus time graph are going to be constant, which means they are going to be flat. Now moving to acceleration. Acceleration is definitely one step up from constant velocity, and acceleration is the rate that the velocity is changing per time, and that is measured in meters per second per second. And when you're changing how many meters per second are changing per second, it is very commonly expressed as meters per second squared. But just conceptually, it's telling you how many meters per second you're adding or subtracting per second to the object. Okay, now keep in mind that has nothing to do with how fast an object is actually moving. It's just the rate at which it's changing. So is it slowing down really quickly or speeding up really quickly? Now, there are three ways to accelerate. You can either speed up, which is obviously increasing your velocity. You can slow down, which is decreasing your velocity, or you can change direction or turn. Now for this one, there are various graphs, just like we saw with constant velocity. There's definitely a lot more going on with these, but there is a position versus time graph, velocity versus time graph, and then acceleration versus time graph. Now for this one, if you have something that's accelerating, it won't have a constant rate of change. It will have something that is curving, something that has a changing slope. Okay, as we said before, when you take the slope of a position time graph, that gives you the velocity versus time graph, and you take the slope of a velocity versus time graph, that gives you the acceleration versus time graph. So same rule applies. Now, if you're taking a look at this slope, it starts out flat, which it's like almost zero, and then it gets progressively steeper in the positive direction. So that means it is speeding up. So something that is speeding up in the positive direction is going to move away from zero and be above the x-axis. If it was speeding up in the negative direction, it would still get steeper, which means it goes more and more upright. Okay, now people will get confused because they'll see a line going down here, but as you can see, it's getting steeper and steeper, right? Because it starts flat over here, and then it has a little bit of a slant, and then it's a little bit steeper here. That's just going faster and faster in the negative direction. So this one would move away from zero, but be under the x-axis to show it's going in the negative direction. Okay, again, when you go from the velocity versus time graph to the position versus time graph, you just look at the slope. This is a constant positive slope, and then the red one is a constant negative slope. Now, the opposite of speeding up would be slowing down. And when you're slowing down, you have something that would maybe be going forward, but not get steeper, but it's going to get flatter. So it's going to rise in the graph and then become more and more flat. So that one's going in the positive direction because it's rising, but it's getting more flat, which means it's slowing down. Okay, so because it's going in the positive direction, we're going to be in the positive region over here, but we're going to make it slow down by starting up here and then moving towards zero. And then on the opposite end, if something is slowing down and going in the negative direction, that means it's getting lower on the graph, but it's also getting flatter. So the rule is if it's getting steeper or more upright, that means it's speeding up in some way. And then if it's getting more flat, that means it's slowing down. You know it's going in the positive direction if it's rising on the graph, and you know it's going in the negative direction if it's going lower on the graph. So my orange one is coming down and it's getting flatter. So it's going down, so that means it's in the negative region over here. And because it's getting more and more flat, it is going to head towards 0 to show that it's becoming progressively slower. And then our green one is a constant negative slope. So it's going to be down here. And then my orange one is a constant positive slope. So it's going to be up here. Now let's take a look at the different formulas from the AP Physics 1 formula sheet. We have velocity equals V naught plus AT. Okay, V is basically the final velocity, so that's sometimes known as VF. And then we have a second formula, which I did write earlier, which is final position equals the initial position, x naught, sometimes written as xi, plus V naught t, initial velocity times time, plus 1/2 a t squared. And then for our final formula, we have final velocity squared equals initial velocity squared plus 2a delta x, which is x minus x naught. Now, with all these different formulas, you have 4 different variables in each one, which means if you were to solve for something and there's 4 different variables, then you want to make sure you have 3 known variables so that you can algebraically find for your 1 unknown variable. Okay, so for example, your red one, you have your final velocity, your v, your initial velocity, your v naught, your a, your acceleration, your t, your time. All of them are the same thing, as in like they have 4 different ones. This one has your final velocity, your initial velocity, your acceleration, and then your delta x. So for any of them, if you have 3 out of your 4, then you can algebraically solve for the 4th. If you are missing something else, then you might have to use a series of formulas or a substitution. Now, the strategy I would recommend is 1, make sure you label your known and unknown variables. Number 2, I would highly recommend drawing a picture with the variables on your picture with arrows, and then possibly including positive or negative values along with your picture. And then number 3, you are going to isolate your unknown variable and then do a little bit of algebra to solve for your unknown variable. All right, so let me show you what this might look like. So say, for example, you have an object that starts at 5 meters per second at a position of 0 meters, and then it travels 20 meters and then reaches a final velocity of 15 meters per second. So then we know our delta x is 20, and then we might be solving for our acceleration. Okay, so what I did is I labeled my known variables where they happened in the situation, as in like the v naught happened right at the beginning. My initial position is right here in the beginning. I did the same thing with my final velocity and my final position, and then I'm solving for my acceleration. Okay, turns out in this scenario, I don't need any positives or negatives. Possibly if this started up high and then went down low, I might have something like a negative displacement. So I drew my picture, I added in the variables. I can put some arrows here. There's not too much going on directionally, but adding some arrows never hurts. And then I see if I need to add any positives or negatives. Doesn't look like I need to. So then I can isolate and then solve for my variable. Okay, so one thing you want to be comfortable with is you want to be comfortable with isolating a variable without the numbers. So you may need to solve for things in variable form. So let me just go ahead and solve for this a in variable form. And if you wanted to add in the numbers later, you definitely could. So if I'm looking at my different formulas, I know for sure I'm going to use the orange one. The reason I know that is through experience and a process of elimination, I see that I have V naught, I have V, and I have delta x. So if I have everything except my unknown variable, then I'm good because I have 3 known variables and then 1 unknown variable. Now, if I were to solve for that, what I could do is I could go ahead and clear myself a little bit of room. And what I would do is I would subtract V naught squared from both sides, and then I have V minus V squared, minus V naught squared equals 2A, and then I'll condense the x minus x naught to delta x. And then what I can do is divide both sides by 2 and divide both sides by delta x, which is basically dividing this by 2 delta x. Okay, and then my a would equal v squared minus v naught squared divided by 2 delta x. Okay, so you want to be very comfortable with moving variables around even if you don't have the numbers and doing something like that. So you might need to report your answer in variable form. If you needed to plug in the numbers, and you go ahead and plug those in and press enter in your calculator and then get yourself an answer that way. All right, now going to free fall motion. That means something that's only under the influence of gravity. So something that only has the force of gravity acting on it and no other force. So the term fall would make it sound like that something is maybe moving downward. Doesn't necessarily mean that. Anything that is moving through the air without the effect of air resistance on it and only the force of gravity pulling on it would be considered something in free fall. So something in free fall has a couple rules that it follows, or a bunch of rules that it follows. If it is rising and it only has a force of gravity acting down on it, then it would definitely be slowing down. So if something is moving upwards and it has a positive velocity, and then it has a downward negative force acting on it, then it's definitely slowing down. Now, the acceleration due to gravity is negative 9.8 meters per second squared, that it's sometimes rounded off to negative 10 meters per second squared. So if you have a positive number, let's say that initial velocity is 50 meters per second and something is tossed up in the air, and you keep on adding negative 9.8 meters per second every second, then eventually it's going to take that 50 and it's going to decrease and continue to slow it down until at its very peak it has an instantaneous velocity of 0 meters per second. So at its peak, it has an instantaneous velocity of 0. Okay, so that's at the peak, the very top of its flight. Now, when it's going down, it follows a similar set of rules, but when it's coming down and it has that same force of gravity that keeps on tugging it downwards, we now have a negative velocity. So if we have a negative velocity and we are subtracting 9.8 meters per second every second, it is going to become increasingly larger negative number, which means that it's going to be speeding up because the direction of the velocity and the direction of the force are working together in this case, and it's becoming faster and faster in the negative direction. Just so happens that if it reaches ground level again, so if it gets popped up at 50 meters per second and then reaches ground level again, then your final velocity would be negative 50 meters per second. Same number and different sign. So the rule is if you're rising, you're definitely slowing down at the rate of negative 9.8 meters per second squared. At the peak, you're going to reach an instantaneous velocity of 0 after you tap 0 and you come down and you're moving down in the direction with the force of gravity and you're working together. You're speeding up and you're still subtracting negative 9.8, or excuse me, you're still subtracting 9.8 meters per second, creating a progressively greater negative number, showing that it's speeding up in the negative direction. Hey, that's basically straight vertical free fall motion. Now, when you add a second dimension to that, now you are going into projectile motion, which is the first time we're taking a look at two-dimensional motion. Okay, now we still have a lot of those same rules. We still have the force of gravity acting on it. We still have an acceleration of negative 9.8 meters per second squared. The way it's going to look is a little bit more complicated and a little bit different. So if we have some kind of initial velocity, what we're going to want to do is we're going to want to break it up into a component, which we can call v naught x, and then we also have a vertical component, which is called v naught y, and then we're probably given some kind of angle theta right here. So as something is moving in this two-dimensional motion, it only has a force of gravity pulling on it downwards. So projectile motion does something interesting to where it's moving sideways, but its horizontal velocity stays completely constant. So whatever velocity that is to begin with, say it's like moving 2 meters per second sideways, it'll remain at 2 meters per second the entire time because there's no forces going in the horizontal direction, which means nothing going directly left and right. We know that force of gravity is going downward, so that is definitely the vertical direction. So our vertical velocity is going to start out great, and then it's become smaller, non-existent at the very, very top because it's not rising or falling for an instant. And then as it falls down, it's going to go faster and faster towards the ground, as we spoke about before. Now, that's everything in the vertical direction. So this one has the force of gravity in the vertical direction, which is going to greatly change the way that it acts. So before we talked about constant motion and constant velocity, that's how this horizontal portion works as it's moving from left to right. And then we talked about accelerated motion, how stuff speeds up, slows down, and changes direction, which our red arrow, our vertical one, shows. As it's rising, it's going progressively slower. It does change direction, come down, and go progressively faster because of that FG acting on it. Now, when you're solving one of these problems, lots of things to consider. First of all, you definitely for sure want to make an X and Y column. So X meaning anything that's going left and right or horizontal, and Y column, anything that's going up and down in the vertical direction. Now, the first thing you're going to want to do is if you have that initial velocity, you want to go ahead and do a little bit of trig, and you're going to end up doing V naught times cosine of the angle to equal your V naught x, and then you're going to want to do V naught initial velocity times the sine of the angle to get your V naught y. The reason why you use cosine is because you want the adjacent side matched up with the hypotenuse, and then for the vertical side, you want the opposite end of the angle matched up with the hypotenuse, and then in the end, you're basically doing something just like this to get your two different components. Okay, now from there, what you're going to do is, let me just go ahead and make up some numbers, and let's just call this 5 meters per second, and then we can call this 10 meters per second. So you're going to place your x value over here, and I'm just going to call that v because on the x end, it's moving at a constant velocity, so there really isn't an initial and final velocity. And then in the y direction, this part is accelerating. Okay, so if you are using the x side, you're only going to use the one constant velocity formula, which is basically v equals delta x over t. And then on the y side, you're going to use the 3 acceleration formulas that we had on that previous page. And what you're going to do is you're going to place your values in the columns that they belong to. You're going to grab your x value and place it over here, and you're going to grab your y value, and then you're going to call that v naught 10 meters per second. Okay, I dropped the y because now it's in the y column, so now it's clear that it's a y value, it's a vertical value. Now, we can go ahead and do that. In addition, we know that's accelerating over here. We discussed that it's a negative 9.8 meters per second squared because of the force of gravity. And now some important values that you may add, this all depends on the situation, is if it comes back to ground level, just like we said for the free fall motion, then your final velocity will be negative 10 meters per second. Now, that might be something valuable that you may use. Again, if something goes up, it arcs like this, just like this green arc, and comes back to the same ground level, then your V naught and your VF are going to be the same values, just different signs. And then what you're going to do oftentimes is the thing that can be put into either of these columns is time, because time does not have a direction. That's just the duration of time that it's in the air that applies to your vertical and horizontal components. Other main things that you might use a velocity, a y velocity of 0 meters per second, because remember, it reaches an instantaneous velocity of 0 meters per second at the very peak. So if it says something about going halfway or to the top of your arc, you may use 0 meters per second. Now, there are a lot of variations for projectile motion problems. So if you want to take a look at more of these variations or examples written out in a lot more detail, then go ahead and click on the link up top. Okay, other than that, that's basically the foundation of how you'll set them up, and everything from there just depends on the scenario you're looking at. Now, let me go ahead and clear some of this space so I can talk about one last idea. Okay, that last idea is this. We have two different velocities that are operating in very different ways on the same thing. What I'm talking about is your picture over here, where you have a vertical velocity, your red vector, and then your horizontal velocity, your blue one. So they're both acting on the same time to show you how it's actually moving in reality, which is this green arc right here. So if it's rising up and moving sideways to the right, what it's actually doing is following this green arc here. So you're using both of those vectors separately. Now, in different scenarios, you might have to piece those back together. And what you're going to use is a little bit of vector addition. So if you want the final velocity of an object over here, what you would do is you would use the tip to tail method. That means that where one arrow ends, the next one starts. So here's my horizontal component of 5 meters per second, just kind of a number I made up off the top of my head for the X direction. And then at the tip of that arrow, I'm going to start the tail of the next one, which is this one, this 10 meters per second. Okay, so if I'm looking for the final velocity over here at the very end, I have one vector to the right and one going downwards, and then my answer is always going to be connecting the beginning of the first vector to the end of my last one, and that resultant vector is going to tell me my actual final velocity. So my actual final velocity isn't this negative 10 meters per second, because that's only my vertical component. It has to be combined with the horizontal one. So if we went and used the Pythagorean theorem of a squared plus b squared equals c squared, you would end up square rooting the sum of the squares of each of the sides, and then you would get the square root of 125, which is about 11.18 meters per second. Now, the very last detail, which is another one that might come into play if you have to add some vectors together, is possibly solving for some angles. And if you need to solve for some kind of angle, you can always use your inverse trig functions. So in this case, you would use an inverse tangent, because tangent is opposite. My opposite is my 10. And then my adjacent is 5. So which is the inverse tangent of 2, because 10 over 5 is 2, and that would give me an angle of about 65.43 degrees. All right, so now that we finished up the more complex details of two-dimensional projectile motion, we are done with our kinematics review, a full dynamics overview that's going to help prepare you for any cumulative test, final, or AP test, especially AP Physics 1. We're going to be taking a look at Newton's first law and third law to begin with. We're going to leave out the second law because that has a lot more problem solving in it. Then we're going to develop the concepts of all the different types of forces and how to draw our diagrams. And then from there, we're moving on to Newton's second law, which brings up a lot of the problem solving and taking a look at those strategies. From there, there's a lot of classic problems and ideas that are related to angles, inclines, and pulleys. So we're going to be taking a look at a lot of those specific problems and the approach you want to take to them. Then we're going to take a look at Hooke's law and springs for a small portion of the video. And then at the end, we're going to be connecting some kinematics with dynamics conceptually and mathematically as well. So let's get started with taking a look at Newton's first and third law. So let's go ahead and start off with Newton's first law. So Newton's first law is also known as the law of inertia, and it states an object will remain in its state of motion unless an unbalanced force acts on it. And its state of motion is going to be one or two things. It's either going to be in motion, which means it is moving at a constant velocity, or it is motionless, which means it's at rest. Okay, and acceleration wouldn't be considered in a state of motion because if it's accelerating, that means it's speeding up or slowing down. So that means it is changing its state of motion because an unbalanced force is acting on it. So the original states of motion are basically in motion or motionless. Now, one thing that we want to make sure we're aware of is what inertia means. Inertia is a property of all masses that describes its tendency to remain in its state of motion. And the indicator for if something has more or less inertia is its mass in kilograms. So it's safe to say if something has 2 kilograms as opposed to 1, it definitely has more inertia, has more tendency to remain in motion or remain motionless. So let's take a look at a couple of examples of Newton's first law to make sure we know how to apply this concept to some different scenarios. Now, say for example, you are moving in a car and the car is traveling forward at 30 miles per hour. And if the car is going forward at 30 miles per hour, that means it and everything in it is moving about 30 miles per hour, assuming that everything is at rest relative to the interior of the car. Now, what happens is if the car brakes abruptly, then the person is going to feel like a force is pushing them forward to the front of the car. Now, with Newton's first law, a lot of times it's actually a lack of force that causes that feeling. So if you're going 30 miles per hour and the brakes are abruptly hit, then it would feel as if you were getting pushed forward, but you're not. You're remaining in your state of motion. So the person wants to continue moving at 30 miles per hour, and they do briefly. And then now the car has actually slowed down. So the car is actually going slower than the person. Therefore, the person would move forward in the car. So because of a lack of force until probably the seatbelt tugs on you, you're going to feel yourself being thrown forward. So that is one example of Newton's first law. Just like if you are sitting at rest and the car speeds up very quickly, it feels like you're being pushed backwards because you remain at rest as the car moves forward more quickly and sort of moves without you temporarily. And that delay between your movement and the car's movement is what you feel as a force pushing you back, although there is no force actually pushing you back. So let's go ahead and take a look at one more car example. And say, for example, this is the top view of a car, and it's going forward, and then it turns to the right. Now, if it turns towards the right, then the car is going to start to get angled like this. And if you imagine someone turning the car really sharply to the right, you're going to feel like you're pushed to the left. But in reality, if you are going forward to begin with, you want to remain at a constant velocity. And a constant velocity means two things. It means you're going the same speed and direction, because velocity has a direction. So if you were going forward at, we'll say, 20 miles per hour, and then the car turns right, it's kind of like it's moving without you. And now if you are continuing on that straight path, you are going to start to bump into the left side of the door, and it's going to give you that feeling that you're being pushed to the left. Again, there isn't any force pushing you to the left. It's everything moving to the right to give you the sort of the illusion that you're being pushed over to the left. All right, so that's basically Newton's first law. Has a lot to do with inertia. And again, inertia is just solely based on mass. So if something has more or less mass, it has more or less tendency to keep on moving or stay at rest. A lot of these scenarios are related to things that are in something else, like a person in a car was the example that I went with. All right, so let's go ahead and move along to Newton's third law. So for Newton's third law, it's every force has an equal and opposite force, and all forces come in pairs. So a lot of times Newton's third law might be stated as every action has an equal and opposite reaction. That version of Newton's third law I don't particularly like, because it sounds like something is happening and then something is happening as a reaction right after, when in fact they're happening simultaneously. So if a person is pushing on an object, we'll say like they're pushing on a big box or a crate, they apply a certain amount of force, and we'll say maybe they're applying 10 newtons of force this way on the box by the person. There is for sure an equal and opposite force in every single case. The box is then pushing back on the person with 10 newtons of force in the exact opposite direction, and this is on the person by the box. Okay, now a common thing that people may ask is, well, if every force has an equal and opposite force, and if you have 10 newtons going to the right and then 10 newtons going to the left, why aren't they canceling each other out? That's because they're on different objects. So if you analyze just the crate itself, and this is these are some ideas that we're going to get to in a moment here with our force diagrams, but we have the force of gravity from the earth pulling the box down. We have something called the normal force, which is the ground supporting the box. And then we most likely have some force of friction going to the left. We'll call that kinetic friction, FFK, which is based on the roughness of the surfaces. So as long as that 10 newtons is enough to overcome the force of friction, then it can be moved. Now, this 10 newtons isn't actually acting on the box itself, so it wouldn't be included with your force diagram on the box. If you drew a force diagram on the person, then it would be involved. So if we're only taking a look at the things on the box, then we have Fn. We have this 10 newtons from the person, which we'd probably call an applied force. We have force of gravity, and then the force of kinetic friction. So this 10 in green is not on the box, therefore it wouldn't be a factor in canceling out this red force over here, 10 newtons to the right. All right, now with Newton's third law, there's a few different applications to it. So there isn't any case where this isn't true. So the word every means that in every single case, there is another force that is exactly the same number, opposite directions. That's where it says all force comes in pairs. A couple other famous examples would be maybe something like a rocket blasting off. And that is a terrible rocket, but if a rocket pushes the gas out this way, then the gas pushes up in the equal and opposite direction on the rocket. So when the rocket is in space in a vacuum where there's no other molecules in contact with it, if it pushes the gas downward, then the gas pushes the rocket upwards. So let's go ahead and label that. So basically what you're doing is if you were to write a little phrase that would describe what happens, you're always swapping the two objects and changing the direction. What do I mean by that? It says rocket pushes gas downwards. So I'm switching the word rocket and gas and then changing the direction to show that it's an equal and opposite force. So the gas pushes the rocket upwards. Okay, so for Newton's third law, there is basically no cases at all where there's not another force pointing in the exact opposite direction. So if things are in contact, and although one thing might be bigger and one thing might be smaller, it wouldn't matter. So if you had a giant 100-kilogram object being pushed up against a 2-kilogram object, that force that they would feel between them would be exactly the same. So if the whole entire system is getting pushed, maybe the blue box feels a force going this way, and then the red one would feel one going this way. In the end, those would be equal and opposite. But if you want to find out what's going on, you just analyze just the forces acting on that particular object. And if you just focus on a single object, then it'll typically be a lot easier to predict what's going to happen. All right, so let's take a look at all the different types of forces, and we'll talk about some details and important concepts related to each of these different forces, and then how to include them in your diagrams. So we have a few common forces that you're going to see. We have force of gravity, which is basically going to be a free force that is the Earth pulling things towards its center of mass. So as far as we're concerned, it's just the Earth pulling everything directly straight down. So it doesn't matter if something is turned on an angle, it is a pull straight down from the Earth in every single case. The force of tension is from any rope-like material, so anything like a rope or a string or a chain, and that is always some kind of pull as well. For an applied force, this one is one that if it doesn't fall in the force of tension category, it would be basically any kind of push or pull from someone or something. As long as it's not a rope-like material, then it won't fall in the category of the force of tension. So applied force is kind of like a larger category. For normal force, the word normal in this case means perpendicular. So it is a perpendicular, and I'll call it a perpendicular support force, but it's not necessarily always supporting an object. But if two things are in contact with each other, there is always a perpendicular force acting. But a lot of times it is from the actual surface itself. And our last one, we have two different ones. We have force of friction, kinetic, and then static. So the word static means at rest, and the word kinetic means in motion. So the one that people are most familiar with is the force of kinetic friction. So anytime things slide along the surface of each other, there is kinetic friction because of the irregularities that are inherently in all surfaces. It's kind of like the roughness of the surface is kind of scraping against each other. So even if it's something really smooth, it still has some irregularities. So there's still some really small bumps that are invisible to the naked eye that interact with each other. And as those go across each other, they provide a force that opposes the slide. So for these, we'll just basically say that these oppose a slide, and kinetic is opposing a slide of something that is actually moving, and then static is opposing a slide of something that is trying to move, but it remains at rest. Now, the force of static friction is always greater than the force of kinetic friction on the same surface. So when something is already in motion, and we'll kind of say it's cruising over those bumps, those irregularities in the surface, and it already has some inertia, it is going to be easier than something that is sitting at rest and sort of, we'll say, stuck in the little bumps and grooves of the surface. So the capacity that static friction has to push back against something is going to be greater than that of kinetic friction. So let's go ahead and take a look at our different force diagrams. So you may be drawing diagrams where you put vectors right on the actual objects, or you may be doing a free body diagram. So free body diagrams are exactly what they sound like. They are not including the actual body or object that you're looking at. All right, so if you take a look at this thing over here, we have a box that's suspended from a ceiling. So we have two rope-like things. Those things would be pulling. So we would have two FTs. You wouldn't just group them up and say we have one FT because there are two different objects pulling on it. So there's two forces of tension, and then there is always a force of gravity pulling straight down. And it doesn't look like we have anything supporting it. So no normal force. There's no type of interaction between a surface of any sliding. So there is no friction involved. And then we just have FT and FG. So if we were making that a free body diagram, we would get rid of the object itself and then just put our forces on a single point, and then that would be our free body diagram right there. Okay, so depending on what you're choosing to do, you can draw the free body diagram off to the side, or you can draw the forces on the actual object, or you could do both if it helps you visually, just sort of help you figure out what's going on with this particular scenario. So let's take a look at this scenario. We have an object that is sliding down a ramp. Now we have the force of gravity straight down, as it always is. So although something is on an angle, it still has an FG straight down. And then it has a normal force because the surface is supporting it. That is perpendicular. So perpendicular creates a 90-degree angle. There's a 90-degree angle right there for our Fn. And then because the thing is moving and sliding, we have a force of kinetic friction that is opposing the slide. Again, if we wanted to do a free body diagram, we would just kind of draw a little dot off to the side and then connect these three forces to it. Now for our last one, we have a person, we'll say, pulling, and then the object is at rest. So if we were to draw the forces acting on the object, we have the force of gravity as usual, pulling straight down. We do have a surface supporting it, so we have a perpendicular force pushing up on it to keep the box from moving up and down. And then if it's being pulled, then we have a force that is an applied force. Like I said, that's sort of a general category. So if we have any push or pull by something or someone and it's not the force of tension, we could probably go ahead and say it's an applied force. Now, if something's being pulled and it's trying to slide and it's not in motion, then there must be another force trying to oppose the slide, and something opposing the slide would be the force of static friction. So it is the irregularities in the surface interacting with the object that is pushing back in the opposite direction. And plus, if it's at rest and we have one force going to the left, then we definitely know that there has to be a force going to the right that would be canceling that force out. So that is the quick overview of all of our different forces and how to add them to each of the scenarios. Once you've had enough practice and experience taking a look at different scenarios, you won't have to necessarily scroll through all these forces, but you'll be able to identify them based on the things that are in contact with the object and also possibly not in contact. Generally, the only one that's not in contact is the Earth for the force of gravity. We're not going to be dealing with any magnetic forces or anything at this point. So most of the other things are because something is in contact with it and interacting with it and pushing or pulling it in some way. So with Newton's second law, it is basically the formula and ideas within the F net equals ma formula. So it's saying that the net force, the overall forces acting on the object, equals the mass times the acceleration, which shows you that the acceleration is proportional to the force and that the acceleration is proportional to the inverse of the mass, which is basically saying that acceleration is inversely proportional to the mass. Now, Newton's second law is the foundation of how a lot of the problem solving related to dynamics works. So let's take a look at a basic example first before we get into some more complicated ones. So when you're taking a look at something, you might have an object, and that object might be pushed to the right by a person, so we have an applied force. And because it's sliding, we have a force of kinetic friction opposing the force. And then we have the normal force perpendicular from the ground supporting the object. And then we also have the force of gravity pulling the object straight down. Now, the way you analyze it is along both of the axes. What I mean by that is you look at all of the forces in the horizontal direction and the vertical direction. Now, the thing is, they might all be pushing or pulling on the object at the same time, but the way that they interact with each other is a little bit different. So we want to make sure we just focus on the horizontal forces, which we'll call that the sum of the forces in the x direction, or we just focus on the sum of the forces in the y direction, which you might call F net x and F net y, but that's all the same thing. Now, what you want to do is if if forces are working in the same direction, you add them up, and if they're working against each other, you're going to subtract them, and that is the net force in a particular direction that gives you the mass times the acceleration. Now, in the x direction, we have the applied force, and then in the opposite direction is the force of kinetic friction, so that equals the mass times acceleration. In the y direction, we have the normal force pushing it up, and then we have the force of gravity counteracting it, pulling it down, and that equals m times a. Now, if you're analyzing it to figure out what the actual acceleration of the object is, you wouldn't necessarily pay too much attention to this usually, because we know that it's not moving up and down. In fact, if it's sitting flat on the surface, then Fn minus Fg equals 0. We know that there's no acceleration in the vertical direction. Therefore, this whole entire side equals 0, so that Fn minus Fg would equal 0, and Fn would equal Fg if you added Fg to both sides. In the horizontal direction, we have Fa minus Ffk, and for that, you'd probably have to get some kind of value for each one of those. For the force of kinetic friction, you may use the coefficient of kinetic friction times the normal force to solve for that force of kinetic friction. In that case, the normal force that you would find over here would be pretty significant. And then from there, you might be finding an acceleration, applied force, a mass, just depends on the problem. Now, moving forward, there's a lot of different scenarios that are going to get way more complex than the one that we just previously saw. For example, if you have an object being pulled on an angle, so say, for example, there's maybe a force of tension pulling it up 30 degrees above the horizontal, and let's say that it's maybe not moving at all. So we have the force of static friction opposing the slide, and then in the vertical direction, we have the normal force as usual, perpendicular upwards from the surface, and then we have the force of gravity from the earth pulling it down. Now, in this case, what you want to do is if you have any angled components, you always break them up into their x and y components. So if we take our force of tension over here, and we'll just kind of create our own little triangle, you would break it up so that it has an x component, which we would call the ftx, and a vertical component, which we would maybe call an FTY. You can kind of label it whatever you want, but just so you can know the difference between the horizontal and vertical components. Now, if you use a little bit of trig, we can find the FTY side because it's opposite of our 30-degree angle. So we would say sine of 30 degrees equals the opposite, FTY, over the hypotenuse, which is our main force of tension. And then in the end, if you cross multiply this over, then Ft sine of 30 degrees would equal your y component. And then in a similar fashion, you would do the same thing for the Ftx, but since the Ftx is on the adjacent side in relation to our 30-degree angle, you would just end up doing Ft cosine of 30 degrees to get your Ftx. Let's go ahead and fix this y. And then you would go ahead and use those two components. Now in the vertical direction, it's going to look similar to our previous problem, but a little bit different. We know that we have two forces upwards. We have normal force, and then we have this force over here, which we call the Fty. So we have two positive ones because they're both upwards. So we'll say the normal force and the Fty are my combined forces in the positive upwards direction. And if you subtract Fg in the negative downwards direction, that would equal 0. We can safely assume that it's 0 because there is no motion in the vertical direction, therefore there is no acceleration. And then in the horizontal direction, remember we have this component over here, which we'd call our Ftx. So if you summed up all the forces in the x direction, then you would say we have an Ftx minus the force of static friction. And then in this particular case, we can also say that it's equal to 0 newtons because the scenario that I gave you was that it was being pulled but remained at rest. That's why it's static, and that static friction is opposing the slide. So in that case, you can also safely assume that it's 0. And then for your force of static friction, you would use the coefficient of static friction times the normal force to get that potentially. And then you would make sure you use some of our previous work like this over here and this over here. So if you were just given that Ft using your sine and cosine functions, we can go ahead and do a little bit more work to find the exact values for Fty and Ftx. And then obviously, depending on the problem, you're going to do some algebra and then solve for your unknown variable from there. Now let's go ahead and analyze an object on a ramp or on an inclined plane, which is a common scenario that's often analyzed in dynamics. And this one is going to work a little bit differently because we will not have an x and y axis that is perfectly horizontal or perfectly vertical. Because we're on a ramp, we won't have any motion in the horizontal or vertical direction. We would have it in the parallel or perpendicular direction. So we can kind of make a new x and y axis, and then we can call this the parallel direction, and then we can call this one the perpendicular direction. If you still want to call it the x and y, that's fine too. It's just sort of like a tilted axis. So what you want to do is you want to make sure all your forces are along this orange dash line or along this green dash line. And then that way we can place it into our x and y formulas when we create our formulas a little bit later after we draw our forces. Now, if we're drawing a diagram here, we have Fg straight down as usual. And we would be given some angle theta over here for the amount of incline for the particular ramp. And then we would have the normal force that it is pushing up perpendicular from the surface of the ramp. And then if it's just sliding down from the force of gravity, then that's all we have unless there is friction between the ramp and the block. So we'll say that there is. In that case, we will go ahead and say that we have the force of kinetic friction opposing the slide. Now what we want to do is our Fg is falling in between the orange and green dash line. So we don't like that. We want it perfectly along this axis, the perpendicular direction or the parallel direction. So what we're going to do is we're going to take a component of it that pushes down perpendicular into the ramp, and we can call that Fgy. And then we'll take the parallel component this way and we'll call it Fgx. Now it turns out that this theta over here always translates to this angle over here. And what we can do is same thing we did earlier. We could use a little bit of trig to find our different components. Now, if you take a look at our theta here, the opposite end of it is our Fgx. So our Fgx is going to equal Fg sine of theta, which is a little bit different than last time because we used the sine of the angle to find the vertical component last time. Now we're using it to find our parallel or x component. And then for the perpendicular component, we are going to use Fg cosine of theta because that is the adjacent side to our angle. And again, these are some more specifics so that if you were to find the FG by doing mg, mass times 9.8, and they just provided the mass, then you would be able to do a little bit of math over here and then find your FGX and your FGY values. So if we were to set this one up, we would maybe have the sum of the forces in the perpendicular or y direction. And then for that one, we have the normal force pushing up. We have our FGY downwards, and again we can safely say that equals 0 because there is no acceleration along this axis over here, along this orange dashed line. And then for the sum of forces in the x direction or the parallel direction, we have FGX that's sending it down the ramp, and then we have the force of kinetic friction that is opposing it. And in that case, we would very likely have an acceleration. So we would have to set that equal to m times a, and then we would either solve for an acceleration or plug one in to find another variable. And again, we may use this formula over here, coefficient of kinetic friction times normal force for our force of static friction, or excuse me, our force of kinetic friction. And then for our FGY, if we wanted this, then we would make sure that we use our work that we set up previously over here. And then if we wanted our FGX, then we would make sure we use this little formula over here. Okay, and again, it all depends on what you're looking for, but that's the general setup and idea of working with an inclined plane. All right, the last type of problem we're going to take a look at is taking a look at some pulleys or a system of objects that may be accelerating together. Now, the method behind these is all fairly similar. You might have something called mass 1 and mass 2. And then if you were to draw the forces acting on them, you would have something like this. You would have the Fg from mass 1. You would have a force of tension from the rope. We'll call it Ft1. And then similar type values for our second one, which we would have an Fg on this one, which we can call Fg2. And then a force of tension from this one, Ft2. Now, the trick to these is basically setting up three formulas, one specifically for M1, one specifically for M2, and then one for the entire system. Okay, so let's just take a look at each specific system first, because that's maybe what we're a little bit more accustomed to. So if we take a look at this first scenario here, we don't have to work along the x-axis for either of them. Everything is going to be vertical, which is nice for us because it'll exclude a little bit of the work. So we have the sum of the forces for mass 2. Now what we're going to do for this one is, because pulleys just redirect the force, we want to make sure we figure out what our positive and negative direction is. Now if M1 is greater than M2, it's pretty safe to assume that M1 is going to win the tug of war between these two objects, and everything is going to move up and around this way. Okay, so we could say that everything that is propelling it in that direction is in the positive direction. So we call everything that's going around in this direction in the positive direction, and everything that's going in the exact opposite direction of that, that is going to be the negative direction. So for M2, we have our Ft2 minus our Fg2, and that equals the mass times acceleration for M2. And then similarly for the sum of forces for mass 1, we have the same thing, but Fg1, remember, is in this direction of how everything flows. So Fg1, although it's downwards, we're going to call that positive in this particular scenario. And then we have that Ft1 counteracting it, and that equals Ma. We'll call that M1A. Now, if you take a look at the entire system, you're going to do something like this. It would look Okay, something kind of like that. So that's not a great picture, but it's just this big blob that includes both of the masses, the string and the pulley. We're just going to assume the only thing with significant mass are the two blocks. So anything that is internal in our system is not going to count for our forces, because there's all kinds of internal forces acting within systems and objects, and those we are not going to concern ourselves with because it's not going to affect the overall acceleration of the system or the object. So the sum of the forces for the whole system is just going to be FG1. See, this is external. This is sticking outside of our big blob, FG1. And then the only other one that's sticking out is FG2. And that is equal to the mass of the entire system, m1 plus m2 times a. Now, oftentimes what you can do with that is you're going to want to solve for the a, whatever number that is, first. Okay, not in all scenarios, but in a lot of them, you're going to solve for the acceleration first, and that is going to be the same acceleration for each of those formulas up top, and then you can solve for a lot from there. So if you're given the masses, or you maybe just keep them in variable form, you have a bunch more to work with if you solve for the acceleration here as a total system and then plug it back into those. Again, it all depends on the scenario in which you're working with, but you're going to want to solve for everything as a whole system and individual pieces for a lot of these. So I'm not going to completely cover all the other ones, but let's go ahead and take a look at them. We might have something like an M1 and an M2 for the rest of these. And again, you would look at them individually and separately. So for this one, if we draw in the forces, we would have the force of gravity, normal force, force of tension, we'll call it FT2, and then we may or may not have friction here depending on the scenario. We're assuming that is going to slide, so we have an FFK. And then for our second one, we have an FG, call it FG1, and then this FG2, since this is mass 2. And then this one has an FT, and we'll call that FT1. Okay. Again, we can set up separate formulas for each one of these, and everything is going to be flowing in a certain direction, which is in this direction. Okay, so that would be considered positive. So if we took a look at our entire system for this one, it would basically just be, let's go ahead and wrap our system up to specifically define what it is. And you could see that all of the forces are internal. This Fn would be sticking out. It just kind of ran out of room, and this Fg2 would be sticking out. But those two are canceling each other and not along the direction of the motion anyways, which would be over and then down. So what you would do is you would say that we have an Fg1 minus the FFK up above in purple, and that equals both of the masses combined times the acceleration. And again, if you wanted those individual formulas like we have in orange and blue over here, it would basically just be the FT2 minus the FFK, and that would equal M2A. And then for our M1, it would be FG1 minus FT1 equals M1A. Okay, again, it's all based off the same idea of this main problem that we worked out over here that's in orange, blue, and purple. Now for our last one, again, it's sort of a similar idea where we would have maybe an applied force here, normal force here, force of gravity, and then let's say this case would be frictionless, then we would have this Ft tugging M1 backwards. And then for our second one, we would have this force of tension tugging M2 forwards. And then same thing as the first one, we'd have a normal force and a force of gravity. So you can do an individual X and Y formulas for M2 and M1 as we did earlier, so I'm not going to repeat that process. But then again, you can treat it like one giant object and then pretend that M1 and M2 are one big system. Okay, in that case, we have these two vertical ones that are canceling each other out, these two vertical ones are canceling each other out. So then in this case, that FA would just equal M1 plus M2 times the acceleration. And then if there was a force of kinetic friction, that would be the opposing force that you would subtract from the applied force. Okay, so main takeaways from this is that you want to make sure you define your system and which direction is your positive or negative. Okay, so the positive is the way that everything is going to flow based on what your scenario looks like, which might change if up or down is positive or negative, or left or right is positive and negative. And then once you have that system defined, you can analyze the system as a whole with the main external forces that are propelling it and opposing the motion. And then that m times a, remember, is going to be the sum of all the masses involved times that acceleration. And then you're going to want to have most likely some individual formulas for your individual objects. In that case, you would ignore your system and pay attention to each of those masses individually and create individual formulas for them, just as I did in orange and blue over here. All right, now two more topics that I want to finish off with, both of which don't have a lot of detail in this overview, but I'll give you a few important points. Now we have something that's related to springs, which is Hooke's law, which we have the force of the spring equals kx. A couple things to know about that is that your k is your spring constant. And it's basically just telling you how stiff or stretchy your spring is. It is how many newtons of force are required to stretch it 1 meter. That's why it's the unit is newtons per meter. So a lot of times, if you don't understand something, if you analyze the units, it may help you a lot in the concept of what it is. So it's the amount of force required to stretch it 1 meter. Now for the second one, our x is basically a displacement in meters. Okay, but it's the displacement of how much it is stretched or compressed. And we'll say from equilibrium. Okay, and by from equilibrium, basically what I mean is what is the length of the spring when it's not being affected by any outside forces? So if the spring is sitting at rest and it's 1 meter and it gets pulled to 1.2, then it's only stretched 0.2. So say, for example, this change in its position is 0.2 meters because it was originally 1 and then got stretched to a total of 1.2, then our delta x is 0.2. There is a negative here because the force of the spring is a restoring force. It's a restorative force, which means that if you're stretching it out this way in the positive direction, it's actually pulling back in this direction, and then vice versa. For a compression is that your delta x would go in the other direction, in the negative direction, and then it would be compressing it and pushing it out in the opposite direction. So there's not too much to that. You may use some of those details and ideas when analyzing springs and taking a look at those formulas. Lastly, when we're taking a look at kinematics and Newton's second law, there's a lot of connections between the two, but mathematically, this is the main one. So if you're taking a look at the sum of forces equal to mass times acceleration, mass wasn't mentioned a whole lot during kinematics, but acceleration is that connecting piece to where if you are looking for an acceleration, you may find it in one of these formulas. So because the main problem solving method is using second law and taking the sum of forces and setting equal to mass times acceleration. In certain cases, you may connect that to kinematics and your three kinematic formulas because they all have an A in them. So one of those A's might be an acceleration that you plug into your acceleration over here, and then possibly work backwards from there to solve for some kind of unknown variable. I'm going to be doing a circular motion review for AP Physics 1, which will also be a good review for any high school physics class or for introductory college classes as well. We're going to cover some main circular motion concepts, talking about how velocity, acceleration, and centripetal force work when you're talking about uniform circular motion. We're going to take a look at some problem solving, some key strategies, where to place certain positive and negatives when setting up your formulas. The key formulas you should be using, certain substitutions that you may be utilizing in those cases, and then also looking at universal gravitation, its relationships, problems, and then tying that into circular motion. So let's go ahead and get started and take a look at those main concepts for circular motion. So with uniform circular motion, we have something that is going around in a circular type motion with a constant speed but a changing velocity. Speed is just the magnitude at which the object is moving, and then velocity has a direction, so the velocity will be constantly changing. Now, if we have an object going around counterclockwise, what's happening is, say for example, they're down here, then they have a certain velocity moving to the right, and that velocity is tangent to that circular path, and then same for every position along the way. So the term that to describe the velocity would be tangent because it's constantly changing, so you can't really say that it's up, down, left, or right, but it just brushes off tangent to that circular path. Now, as something is moving to the right, in order for it to start turning to the left, there has to be an unbalanced force that acts on it, and it turns out that if you have a force pushing something to the left, pushing or pulling it to the left, and you have velocity going to the right, then you're going to move in a path somewhere in between, something like that green vector right there. Now, the force that's going towards the center of the circle is known as the centripetal force. That is the main driving force that causes objects to go around in a circle. So let's go ahead and write this down on the side. The centripetal force is actually not a new force. So at this point, you probably are pretty familiar with forces: the force of gravity, normal force, force of friction, etc. The centripetal force isn't a new force of its own. The centripetal force is actually the force of gravity, force of friction, the normal force, and then so on. Okay, so what is centripetal force then? Centripetal force is just a force that's directed towards the center of a circle. So centripetal is actually a direction. Okay, and that direction is center seeking. So again, if you're going around in a circle, the direction of this red vector is going to change, but it's always pointing towards the center of your circle. So a centripetal force is basically the force, which may be force of gravity, friction, etc., that is pushing or pulling towards the center of the circle and constantly making an object turn. So if we go over here and we're taking a look at our velocity vector that's taking us upward on the screen, if we have a force pushing or pulling towards the center of the circle this way, then it's going to cause it to start turning in this direction, and then so on. So we have a centripetal force going down this way, the object turns this way, and then same for our last position. So when you're going around a circular path, as I mentioned before, if you're talking about uniform circular motion, then you have a constant speed, but a changing velocity. Oftentimes people think you need to change velocity by increasing or decreasing the magnitude of that number, but not necessarily, as long as you are changing the direction. And in this case, it is because you are changing direction. So when something is constantly changing direction, then it's considered to be in accelerated motion. So because it has changing velocity, it is accelerating and has something called a centripetal acceleration. And that centripetal acceleration is basically how quickly an object is changing direction. So if something is going around, in this case, as we saw before, it's going counterclockwise. So the faster it's moving, the faster it's going to be changing direction. So we're not necessarily looking at its actual velocity of how many meters traveling per second, but more so how quickly it's changing direction. All right, so we have our basics covered. We have a velocity, we have some inertia, and with the combination of the velocity and a centripetal force, it's going to constantly cause an object to turn. And while it's turning, it is changing direction. Therefore, it is accelerating. It has something called a centripetal acceleration because it has an unbalanced force acting on it. Now, let's go ahead and take a look at some problems. So let's take a look at three circular motion problems, all of which are pretty different. One of them is going to be a person going around a roller coaster loop. The second one is a car turning in a circular path. And the third one is a ball hanging from a string going around in a circle around a pole, which would be called a tetherball. So what you're going to do is you're always going to start out by drawing your forces on the object that you're focusing on. So if we're taking a look at the person is going to have a force of gravity, and they're also going to have a normal force upwards. And then that normal force is the seat applying a force upward in the perpendicular direction, and the force of gravity is a pull down by the earth. Now, if the person is at the top of the loop, they still have a force of gravity because they're still pulled down by the earth, but their seat is facing downwards, so they have a normal force also pointing downwards because that is the perpendicular force being applied by the seat. Now, the way that circular motion works is we are still basically using Newton's second law, and Newton's second law says the sum of the forces equals the mass times the acceleration. And then one of the key differences is that with circular motion, your centripetal acceleration is v squared over r, the velocity squared over the radius. So the way you set it up is going to be pretty similar to the problem solving that you would do for forces or dynamics. We're going to combine all the forces by adding or subtracting them based on their directions and set that equal to ma. In this case, ma is mv squared over r. Now, the key thing is this. When you're taking a look at circular motion, you are focused on the centripetal force, so things that are pointing towards the center of the circle. So we already identified that the force pointing towards the center of the circle is a centripetal force, cause it to go around in a circular path. So anything going towards the center of the circle would be considered positive, and then anything pointing directly away from the center of the circle would be considered negative. So with that in mind, let's go ahead and set up the formula for the person at the bottom of the roller coaster. So at the bottom position, we have the normal force, which we'll call positive because it's pointing towards the center of the circle. So it's increasing the rate that the person is moving around in this circular path. And then we have the force of gravity, which is actually pointing exactly opposite that direction. So it is in the negative direction, and that equals mv squared over r. In the top position over here, it's going to be a little bit different. We have the force of gravity and the normal force pointing towards the center of the circle. So the force of gravity and the normal force would be considered positive. So you would set both of those equal to mv squared over r, or the sum of both of those, excuse me. Okay, so that is the key difference in solving for the bottom and the top. In a lot of your problems in general, you're going to go ahead and draw your forces. And if things are pointing directly towards the center of the circle, you make them positive. If they're pointing directly away from the center of the circle, you're going to make those negative. Now from there, just depending on what you're solving for, you're going to use a lot of the same basic concepts we've used before, which is doing mg for force of gravity. And also one of the key formulas or substitutions you may use is for the velocity. The velocity is going to be 2 pi r over t. Okay, what that is 2 pi r, 2 pi times the radius is the circumference of the circle. So it's basically just the distance of the circle itself. And then capital T is the period. It's the amount of time it takes to complete one full circle. So it's a little bit different than the lowercase t, which is just the regular amount of time elapsed. Capital T, as I said before, is the period, the amount of time it takes to complete that circle. So this velocity is basically just giving you a certain rate at which it's completing that circle. So oftentimes you may need to take that 2 pi r over t and then slide it in to where that v is. Okay, when you do that, the way it's going to look is something like this. So just to give myself a little bit more room, I'll do that substitution right over here. And if I did do that, I'd have this m, so I'd have the mass, and then if I'm squaring the entire thing, 2 pi r over t, 2 squared is 4, pi squared is just pi squared, then we'd have r squared, and then we'd be squaring the period, which is going to drop into the denominator, and then we have this little r over here. Okay, so then we could cross out one of the r values, one on the top and one on the bottom, and then if we wanted to solve for a period or plug in a certain period, that's what it'd look like once you do that substitution. Okay, so let's go ahead and take a look at our last couple problems. I'm not going to go through too much of the full setup now that you've seen the main concepts behind the problem-solving strategy, which is over here, recognizing the positive and the negative, and then also doing the substitution of the v squared over r and the 2 pi r over t. Now, with this car problem, this is the rear view of the car. So it's not a great picture, but this is the back view of the car, and we'll pretend it's going into the screen and then taking a left. In that case, we have the force of gravity straight down. We have the normal force perpendicular straight up from the street. And then as it's turning, because it has the tendency to try to slide to the right, then it has a force of friction keeping it from sliding out from the circle. So your force of static friction is your centripetal force. There is nothing to add or subtract from the force of static friction because that is the only one that's pointing towards the center of the circle or away from the center of the circle as well. So you would just say the force of static friction equals mv squared over r. And if need be, you may use the formula mu Fn, the coefficient of static friction times normal force, to get that force of static friction. All right, now going into our last problem, this one is slightly more complicated. Again, we're focusing on just things that go directly towards the center of the circle. So if you have a tetherball problem where something is hanging from a string and swinging around a pole, if you looked at it from the top view like this, that's how you would see your actual circle. So the center of your circle is actually the pole itself. So if we were to draw our forces acting on the ball, then we would have the force of tension going diagonally upwards to the left. We would have the force of gravity straight down, and that would be it. Okay, so it's a little bit harder to identify the centripetal force. So you want to make sure you take any angled force and break it up into its components, which is pretty typical when looking at forces. And we'd have a force of tension in the x direction, and then we'd also have a force of tension in the y direction. So our force of tension in the x direction is going to end up being our centripetal force. It's the only thing pointing directly towards the center of the circle, and there is nothing pointing away from the center of the circle, so we don't have to subtract anything. So that equals mv squared over r. All right, so now we have covered all the main concepts for what circular motion is and how velocity, acceleration, and force work, along with taking a look at some problems and some strategies. Now let's go ahead and take a look at the universal law of gravitation. And once you get to this level of looking at gravity, it basically tells you that all masses have gravity that are directly related to the amount of mass in the object or the amount of matter that composes it, and also inversely related to the square of the separation distance between the two masses. So if you have two different masses, they will both have a force of attraction towards each other. That force of attraction, you could draw it from the actual center of the mass or center of gravity from the object, but it's always an equal and opposite force as usual. So you would just plug in the mass of one object, the mass of the second, and then plug in that separation distance. Again, that separation distance is technically from the center of mass from both of those objects. And then you have a constant 6.67 times 10 to the negative 11th that you're going to plug in for that problem every time. But that's basically how you're going to solve for that force of gravity. So going back to these relationships over here, these are some key relationships in understanding how the force of gravity gets changed from mass and radius being the separation distance, this r value over here. With mass, it's pretty straightforward. If you have exactly double the mass, then you're going to have exactly double the force of gravity. Say, for example, you have 3 times the mass for one of them and 4 times the mass of the second one. Then 3 times 4 is 12. You'd have 12 times that force of gravity. So that's a direct relationship between the force of gravity and the mass. Now, for the separation distance, it's an inverse squared relationship. So what that's going to look like is if you have 2 times the separation distance, then you're going to have 1/4 of the force of gravity. It's inverse, so that would be 1 over 2, but then inverse squared. So we're going to square that 2, which makes it a 4. So same thing if it were, we'll say 4 times the separation distance. Inverted would be 1 over 4, and then 4 squared would make it 16. Okay, so that is a common the couple common relationships to be looking at. Sometimes multiple things might happen. For example, you might double one of the masses and you might double the separation distance. If that happens, then you have 2 times the FG divided by 4. 2 over 4 is 1/2. And then if you combined those two, then you would have 1/2 of the force of gravity. Okay, so there may be combinations where there are things affecting the masses in your numerator and then the separation distance in your denominator. Now, there's a couple other common problems. One of them is finding a little g value. So when you're taking a look at this formula, it was set equal to Fg. And then in a lot of the previous work you've probably done, Fg equals mg. And that m would be like the actual object itself. So say, for example, you're talking about, we'll change these subscripts here. So mass of a person, and then the other mass is the mass of the Earth. Okay, then this would be the mass of the person experiencing a certain amount of gravity on Earth, and the mass of the person cancels out. So if you want the little g value and you plug in all these values over here, then that's where you get 9.8. So if you wanted to find a little g value on a different mass, say for example a different planet or a moon, that's basically what you do. You set gmm over r squared equal to mg, and then the mass of the actual thing on the larger mass is the thing that drops out, and then it turns out that it's only the mass of the actual larger body that matters in determining that little g value. Now moving on to one of the last big topics with universal gravitation and circular motion, that topic would be things in orbit. Now, say for example, you have the Earth and the moon revolving around the Earth. We have the moon taking a circular path. If we were to draw the forces on the moon, as my picture stands, it only feels the force of gravity on the moon by the Earth, and then the Earth feels the force of gravity on the Earth by the moon. And then again, forces of gravity is always two forces of attraction that are equal and opposite to one another. Now, if you notice, if we're analyzing the moon, we have a force of gravity that is pointing towards the center of the circle. So the force of gravity is the centripetal force. So if we're combining a couple of our ideas, the force of gravity is gm1 m2 over r squared. And then our centripetal force is mv squared over r. Now, again, I can go ahead and change these subscripts a little bit because we're looking at a specific scenario. So this would be the general look of something that's in orbit. And then when you analyze it a little bit further, we can go ahead and change these subscripts. So this is the mass of the moon. Here's the mass of the moon, and then mass of the Earth. So the force of gravity, the force of attraction, is between the moon and the Earth. They have a certain separation distance. That separation distance, as I said before, would technically be between the center of gravity of both objects. So basically right in the center of the Earth and the center of the moon. And then the thing going around in a circle is the mass of the moon, or is the moon, but that's why we have the mass of the moon. So it turns out that the mass of the actual thing going around in a circle is irrelevant. It doesn't matter if it's a moon, a satellite, or an astronaut. We are just going to be left with our constant g, the mass of the Earth, r squared, v squared, and then r, and then also one of the r's actually drops out as well. So then you can solve for things a little bit more easily. And another common thing that you may do, which we mentioned before, is that velocity is 2 pi r over t. So if we know the period, which is the amount of time it takes to complete that full circle, and the radius, then we can go ahead and solve for that velocity and plug it in there. I'll be doing an energy overview useful for AP Physics 1, but any high school level physics class or introductory level college classes as well. We're going to be taking a look at all the different types of energy, the different variables and concepts related with all those different types of energies, taking a look at different relationships within each of those formulas, and then taking a look at how work and power are related to all of those things and one another. Secondly, we're going to be taking a look at some different systems and how to analyze systems and define systems. And along with that, we're going to be taking a look at the conservation of energy and then how work is added or subtracted to these systems. Finally, we're going to be taking a look at the problem-solving process and basically how to analyze a certain situation and use certain strategies in order to successfully solve for unknown variables. All right, so let's go ahead and get started and take a look at some different types of energy. So one of the main types of energy is kinetic energy, the energy of motion. And kinetic energy is oftentimes represented by either a KE or K. And for kinetic energy, that is equal to 1/2 times the mass times the velocity squared. So the relationship between mass and kinetic energy is one of a direct proportionality. And then for kinetic energy to velocity, that is a squared relationship. So as the velocity rises, the kinetic energy is actually going to rise exponentially. For example, if you were to double that velocity, then you would get 4 times the kinetic energy. And then if you were to triple the velocity, you would get 9 times the kinetic energy, and so on, because if you were to place a 2 or a 3 in front of that v, it'll eventually get squared and give you an exponential rise. Now, with kinetic energy, because oftentimes the mass is unchanged, the main variable is definitely going to be that velocity, so how fast the thing is moving in the problem. And then secondly, one of our main types of energy is gravitational potential energy, which is oftentimes written as UG or sometimes written as PE with the subscript G. And that is solved for by doing mgh And then all of those are direct relationships, and then G is the constant 9.8. And this one is similar to kinetic energy in the sense that the mass is usually fairly constant. The G is a constant, so H is our determining factor in telling us if we have more or less gravitational potential energy. Next in line, we have another type of potential energy, which is called elastic potential energy. And this is known as UE or PE with the subscript E. And this is 1/2 kx squared, where k is a spring constant. It doesn't necessarily have to be a spring. It could be something like an elastic band. So a spring constant is how many newtons of force is required to stretch that object 1 meter. So basically how like stiff or stretchy a certain spring is. And then the x value is a displacement value, but it's the amount that it's stretched or compressed from its equilibrium position. And there's one more formula that I'm going to throw in there. There is a second formula, and is for gravitational potential. And that one is negative Gmm over R, G being the constant 6.67 times 10 to the negative 11th. And then these are just two different masses, which we'll maybe call M1 and M2, separated by a certain distance. R is going to be that separation distance. And you would only use this formula if there is a changing G value. So in most cases, in a very, very high majority of them, you're just going to be using MGH and then using G value of 9.8. If there's some cases where something is moving away from the Earth and it's moving into space, and there is a changing G value, and then you have something that's moving a really, really great distance away from the Earth or the surface of a large body, you may be taking a look at this formula for some conceptual and mathematical ideas. Now, the next couple ideas we're going to be taking a look at are work and power. Work is a fairly large idea, and to sum that up simply, it's basically the amount of energy transferred. And the formula to solve for work is work equals force times distance times the cosine of theta. So if you have a theta involved, taking the cosine of the angle may be a factor in solving for the proper amount of work. So because work is basically finding a certain amount of energy transferred, which is something that's either added or subtracted from an object or system, you are talking about something that is still measured in joules. And we have the force and distance. It's the amount of push or pull from an object measured in newtons. And then the distance or displacement is how much it is moved in meters as usual. When you're taking a look at power, power is just bringing in another factor, which is power is the work over time. Oftentimes they are closely associated because power is basically the rate that work is done. So it's basically how fast the energy is being transferred. So finding work is just the amount of energy that is transferred. Is it 10, 20, 30 joules? And then power is talking about how many joules per second is being transferred. So with power, you can look at it one of two ways. You can take a look at it in its standard unit of watts, which is a capital W, not to be confused with this lowercase w, even though you probably can't really tell this is a lowercase w. It is. But watts is a capital W. Again, is the amount of energy transferred. Energy is measured in joules, and time is measured in seconds. So it's how many joules per second are transferred. And a watt is a joule per second. They're basically the same exact thing. Watt is just the condensed version from James Watt's last name. Next, we're going to be taking a look at three different similar scenarios where we're going to define our systems. And defining our systems is going to be a key step in the analysis of all of our energy problems. So if we're taking a look at our system, for our first case over here, we are going to want to include a few things in our system, and I'm going to have some different things include our system, which are going to change the approach of each of these problems. So in our system, we are going to have the block, the ramp, and then also the earth. Okay, although you normally don't really pay attention to the earth because you don't see it directly in the problem, the earth is going to be definitely involved because the force of gravity comes from the earth, so you wouldn't have any gravitational potential energy without it. So we're going to go ahead and include the earth in that system. Now, if something were to be sliding down the ramp, then all of that energy would be conserved within that closed system. So if the system started with a certain amount of initial energy, it would definitely have the same amount of final energy because all of that energy is within that closed system. So we have gravitational potential energy, we had to have a little bit of kinetic energy going on, and then if there were friction, then it would transfer heat to the ramp, but the ramp is all part of that system. So all of that energy would stay within the system. So if in combination, all of that stuff happened to be 100 joules of energy, although it would be redistributed in a bunch of different ways, you would still have 100 joules of energy at the end. So let's take a look at a different system and see how that would affect our results or our analysis a little bit. Now, let's say, for example, we have that same exact system, except we have a block and we have the earth. Now, if it were to slide down and if there were friction and heat were created and it was transferring energy to the ramp, then the block itself would end up slowing down and losing some kinetic energy. So in this case, there is negative work being done on the system by the ramp. So I'm going to go ahead and put the subscript ramp over here. So if you were to analyze the system, would the initial energy of the block and earth together equal the final energy of the block and earth together? That definitely would not, because it gave some energy and transferred some to the ramp. So what you would do is you would have an initial amount of energy and you would have a certain amount of energy that is transferred away from it. So you're going to subtract a certain amount. And then after that amount is taken out, that is your amount of final energy because you have given some work, you've given some energy to the ramp. Therefore, the block itself is going to be losing some energy. Therefore, the final energy is going to be a little bit less. So just kind of making up some numbers, maybe we have 100 joules over here, and then you gave up 20 joules of thermal energy because of the friction to the ramp, and then now you have 80 joules of energy final with the block and the earth. Now for our final one, let's go ahead and take a look at our system one more time. In this case, I included a person applying a force pushing something up the ramp. So maybe we have the block, earth, and ramp in our system. And then we're going to have a certain amount of gravitational potential energy and kinetic energy at certain points of it. But if we take our initial energy and we set it equal to our final energy is actually going to be greater. So why is that? Is because that there is work being done by the person on the block, which means that they're adding energy into the system. Okay, so you would add a certain amount of energy in there. So maybe there's 100 joules of energy initially, and then the person put in 30 joules of energy, and then in the end, the block, earth, and ramp system ended up with 130 joules worth of energy. So in some cases, you will be the one defining the system. Actually, in a lot of cases, you'll be the one defining the system. So you want to make sure you have a clear definition of what your system is and then proceed from there. Certain problems may define the system for you, and then you have to follow the parameters of which they set. And then you may have cases where you have work being done by something that is creating energy leaving the system and done by something that is creating energy or putting energy into the system. Now, the next thing we're going to do is we're going to take a look at a roller coaster problem and talk about total mechanical energy. And we're going to go ahead and analyze this roller coaster, talk about mechanical energy and some of the details associated with it. And then we will end off by doing a full analysis of a complicated energy problem that involves all the different types of energy. So, what mechanical energy is, it is the sum of the kinetic and potential energies. The potential energies could be elastic potential energy and gravitational potential energy. In the case of a roller coaster, we don't have any elastic potential energy. Now, the rule is once some work is done on the roller coaster by the chain lift, the roller coaster cart itself has a certain amount of mechanical energy. We'll call this MEI. At the very top, it will have pretty much all gravitational potential energy, and then it will not have any kinetic energy right before it drops. In reality, it probably has just a little bit. That total mechanical energy is going to stay constant in this closed system as long as we are treating it as an ideal system that doesn't have any factors affecting it, such as air resistance or friction. These forces, such as air resistance and friction, are called non-conservative forces because they are path dependent. Basically meaning if they take a longer or shorter path, that's going to affect the amount of energy that they give or take from a system. In most cases, they're going to take energy from an actual object and slow it down a little bit. Okay, so if we're taking a look at this ideal situation where it is a closed system with the cart, the track itself, and then also the Earth providing that gravitational field, we have a constant amount of mechanical energy. In the beginning, it's all gravitational potential. At this point over here with this loop, it's not quite as high off the ground. We'll go ahead and call this baseline here about 0 meters. So we're going to have a little bit less gravitational potential, but we will definitely have a little bit more kinetic energy. And then in our very last spot over here, we're going to have even less gravitational potential because we're a little bit lower, not as much height off the ground. So we're going to have a small UG, and then we're going to be going a little bit faster. We're going to have a greater K value. Now, in the end, the sum of the kinetic and potential energies is always going to equal the same. So again, if I go ahead and make up a number, let's just pretend this is 100 joules in the beginning. They are going to be, that 100 joules is going to be distributed differently between our two different types of energy. Now, it depends on that very specific height, but it'll look something like this. Maybe we'll have 40 joules of gravitational potential energy here. So we would have 60 joules of kinetic, and then over here it's a little bit lower. So maybe we'll have 20 joules of gravitational potential and then 80 joules of kinetic energy. And then that is showing that the sum of the K and the U values is always equal to 100 joules. As I said before, we have a constant amount of mechanical energy because we're looking at an ideal situation that doesn't have any non-conservative forces acting on it. If there were, then that mechanical energy wouldn't be consistent. All right, so let's go ahead and move on to our final question that's going to be a lot more detailed and involve all the different types of energy. All right, so let's go ahead and take a full analysis of an energy problem that involves all the different types of energy: kinetic, gravitational potential, and elastic potential. So in this case, if there is a coefficient of kinetic friction, that means that there is going to be some energy transferred to the ramp. Now, what you're going to do is you're going to use the work energy principle or the work energy theorem. Now, that's basically what I did in the previous screen. And what that looks like is the work is equal to the change in energy of the entire system. If you find the change in energy of anything, it's always the final minus the initial. So E final minus E initial. And in my opinion, conceptually, I think it's a little bit easier to look at it in terms of adding initial energy to both sides, which would cancel it from this side and add it to our left side. And then you're basically saying this is just the conservation of energy. Whatever initial energies you have, that is going to sum up to the final energies. And if there's a difference in those two, it's because you are adding or subtracting a certain amount of work. I just put plus W because that W might just be a negative value. Now, when you expand that out to all the different forms, that might mean you have some initial kinetic energy, that might mean you have some initial gravitational potential energy, or some initial elastic potential energy. You may or may not have some work, so we're going to take a look at that. And then in the end, you'll potentially have some kinetic energy, some gravitational potential energy, and some elastic potential energy. Now, what you want to do is just ask yourself a series of very simple questions. So let's take a look at our scenario over here. Over here, we have a block that's compressed against a spring, and then when released, it's going to go down the ramp. And then this is going to be our starting position. We'll call this position A. And then this will be our ending position. We'll call this position B. Okay, so at position A, we're going to answer a series of simple questions, which is the block moving? When it's compressed against the spring, the answer is no. So I'm going to go ahead and cross that out. UGI, does it have an initial height? Now, you get to set the baseline of what the height of 0 is. So I'm going to set that baseline right here and call this 0 meters. Now, if you wanted to call this top point 0 meters, then you can call the height going downwards a negative height, which most people typically wouldn't do, but you get to set your baseline of what 0 meters is. So you definitely want to do that at the beginning of the problem as we just did. Okay, so does it have some initial height and some initial gravitational potential energy? It definitely does. It's off the ground. And does it have something that is stretched or compressed in the beginning? It definitely does. Okay, is there some work being done? Because I was given a mu sub k, I would say yes. At the very end, when it reaches the bottom of the ramp, is it going to be moving? It will definitely be moving. Is it going to have any height off the ground? It will not anymore. And is anything stretched or compressed? Nothing is stretched or compressed anymore at this point. So what you would typically do is you would expand everything out into its full formula. So you would have mg h naught or hi, and then 1/2 kx squared plus the work. And the work is going to be the force times the distance. And if you wanted to find the force, you would actually find the force of friction. So for this one, it'd actually be slightly complicated. So let me go ahead and draw the block over here. And you're going to want the normal force. So we're going to have this mg, and then we're going to have an mgy and an mgx. The mgy is going to be our perpendicular component to the ramp, which is equal and opposite of the normal force. So if we want to find the force of friction, which is mu times normal force, our normal force would be mg cosine theta. And then you would place that in where the Fn is. All right, so that's what our work would be. And then on this side over here, we would have 1/2 mass times the final velocity squared. So from there, you're just going to go ahead and solve for whatever you would need to. It all depends on what you're looking for as your unknown variable. A lot of times you may be able to cancel out the mass if there's only kinetic energy and gravitational potential energy involved, because all those have an m value in them. But if it has a elastic potential energy or a work value in there, you're not able to do that. You're going to have to make sure you include all of those variables within it. All right, so that's basically a problem solving process. You're going to start off with this setup right here, and you may or may not have work depending on what kind of problem you're looking at and what kind of system you're looking at. If you take the initial and final energies and then you expand it out into all the different types of energies there are, you can use that and ask yourself a series of questions like, are they moving? Are they off of the ground? Is anything stretched or compressed? And everything you say no to, you're going to go ahead and cross out. And everything that you leave there, you're going to expand it out into its full formula. And then obviously do some rearranging and some algebra to solve for your final unknown value. We'll be doing a full momentum overview for AP Physics 1, which will be a good review for any high school physics class or introductory college classes as well. We're going to be checking out what momentum is and impulse, taking a look at those concepts, formulas, and a couple graphs. Then we're going to move on to different types of collisions and taking a look at conservation of momentum and energy. And finally, we're going to be taking a look at the problem-solving methods, strategies, analyzing different kinds of collisions, and making sure we can distinguish between them based on descriptions and numerical values as well. So let's go ahead and get started and talk about what is momentum and impulse. So momentum is the amount of motion that an object has. Oftentimes it's also described as inertia and motion, and both of those definitions aren't really great for getting a full understanding of what it is, but when you take a look at the different formulas and applications of it, that's where you really develop that conceptual understanding of it. So momentum is represented by a lowercase p, and it is the product of mass and velocity. And to show the amount of motion of an object, how much stuff is it composed of, is the first factor, which is mass, that is measured in kilograms. And then the second factor that is significant is how quickly that mass is moving in meters per second. Now, for momentum, it doesn't have its own special unit. You actually just take these two and combine them, and you get a kilogram meter per second. So it's basically after you get the product of the mass and the velocity, you combine those units as well. Now, when you're taking a look at impulse, impulse is a change in momentum. So change in is shown with the symbol delta. So delta P, the change in momentum, is impulse. Sometimes it's also shown with a J as well, but delta P, I believe, is a little bit more common. So when you're taking a look at impulse, you can take a look at it one of two ways. If you want to find the change in anything, you can always do the final minus initial value. So you can take the final momentum minus the initial momentum, which we'll call P naught. And if you wanted to find that delta P, then you could do mv final minus mv naught, which is the initial velocity. And then if you factor out the m, then you have vf minus v naught. Okay, that's one of the formulas that is not on the AP Physics 1 formula sheet, but it's basically just taking this formula mv and using it twice to find the change in anything. So the one that is provided looks like this. It is the change in momentum equals the force times the change in time. And we're probably pretty familiar with force at this point, which is how much something gets pushed or pulled in newtons, which is a requirement to cause an impulse. So an impulse is basically a force acting on an object that changes its velocity, therefore changing its momentum. Okay. It could also change its mass, which is much less likely. So typically it's a change in the velocity like we see here, Vf minus V naught. And then our delta T is the time of impact. So that time of impact is typically a little bit shorter than our regular time. Our time elapsed normally might be something like 7, 8 seconds, 30 seconds. A time of impact, say for example, a baseball bat hitting a baseball, that could be something like 0.02 seconds. So a lot of times that time of impact might be fairly small. Now, there are a bunch of relationships associated with this formula. So if you go ahead and take a look at this formula and rearrange it to solve for force, then it looks like this. It becomes delta P over T equals F. So the more impulse you have, the more force you have, and the more time you have, the less force you have. That is the main that's one of the main relationships in there, is that if there's more time of impact, then you decrease the force, and then vice versa. If you have a smaller time of impact, then the force rises. Okay. For example, if you are catching something, if you move your hands backwards while you're catching it, if you're catching something fragile like a water balloon or an egg, and you move your hands back with it and create a little bit more time of impact as you're stopping it, then you decrease the force greatly. Just like if you take an egg and you drop it on the concrete, it gets stopped very, very quickly. That time of impact is extremely small, so that force is extremely large. But if you took that egg and you dropped it into a pool of water, it would give it much more time to stop and that greater impact time. will decrease the force greatly. The second thing to look at would be this. If you were to increase the impulse, you're basically increasing the velocity. So that could be done one of two ways. The first way is a little bit more obvious. If you want to hit something faster and farther, if you hit it with a greater force, that is going to help create more velocity and a greater increase in momentum. But the time of impact is one of the parts that people don't often think about. So if you want a greater impulse, you can either one, increase the force, which is pretty obvious, like I said, or increase the time of impact. So a lot of times when they talk about following through and then creating that impact time or increasing that impact time, that is going to increase your impulse and increase your velocity overall. And then there's one more idea that is fairly common with impulse, and that is looking at it graphically. So if you take a look at a graph that is a force versus time graph, if something receives an impact from an object, which could just be a wall, a person, just any object of any sort, um, what might happen is that force might spike and then drop back down. And if you see any kind of force versus time graph, so let's go ahead and put force versus time there. What you can do is if you find the area beneath the curve, that's going to give you the impulse. Okay, the reason why that would give you the impulse is because when you take the product of force and time, as we saw over here in red, that is going to give you the impulse. So if you find the area of this, that is going to equal your delta P. So you would just basically use, 1/2 base times height if it's some kind of triangular space like that. But whatever the case is, if you find the area underneath the curve for any force versus time graph, that is going to give you your impulse. Now, with momentum, you are largely going to be looking at a lot of collisions typically, and there's something called an open versus closed system. A lot of times you're analyzing a closed system. A closed system is a case where that there are no external forces influencing your system of objects, therefore keeping the momentum constant within that system. If it is open, then there is a change in momentum for the entire system. So typically when you're taking a look at a collision problem, it's something like this, where the total momentum before the collision equals the total momentum after the collision. Now, two large categories for collisions are elastic. Let's fix that. Elastic and inelastic. So for both of these, momentum is conserved. Which means this right here is the total amount of momentum of all objects within our system before the collision and after the collision will be exactly the same. But the difference between them is that energy may not be conserved. So for elastic, your total energy is conserved and you'll have the same amount before and after the collision. For an inelastic collision, your total amount of energy is not conserved. So those are going to differ. So it's usually the total amount of kinetic energy in the beginning does equal the total amount of kinetic energy after the collision, and for this one it does not. Now between the two, a lot of times elastic is called a bouncing collision, and then inelastic is called a sticking collision, where the two masses combined. So it does do this sticking if it is perfectly inelastic. And that's where you'd use that term. So if you hear the word perfectly inelastic, that means they are going to stick together and combine masses. But in any case where the momentum is conserved, but the kinetic energy is not conserved, that would be considered inelastic. And then for our elastic collision, everything is conserved as far as energy and momentum are concerned. And with these, they are hitting each other and then they are separating after the collision, not necessarily bouncing in different directions, but we'll just say they're separating after the collision. So when you're given a scenario, typically it's going to be in the form of a word problem. Sometimes there's going to be some graphics there. So the first thing I would do is I would highly recommend drawing everything before and after the collision. And there's many reasons for that, which I'll explain as we move along. So say, for example, we have two spheres, a 2 kilogram sphere and a 1 kilogram sphere that are colliding with each other. So if they're moving towards each other and colliding, we are going to make sure that we label them as before and after, as in before the impact and after the impact. Now, based on our description, we're going to get some certain values here. So let's say, for example, this one's moving at 2 meters per second to the right, and this one's moving at 3 meters per second to the left. That is going to indicate that we're going to want to put a negative sign if we have something in the opposite direction. And then for the 2 kilogram object, maybe afterwards it slows down and it goes down to 1 meter per second. And then we're going to find what the velocity is for this object. Okay, so we're going to do a few different things. Number one, we're first going to solve for the final velocity of that 1 kilogram object. Number two, we are going to figure out what type of collision it is. If it is elastic or inelastic, sometimes people would just jump to the conclusion that it's elastic because there are two things that are bouncing off of each other. And then number three, we're going to do the problem in a different way with a different perspective using impulse. So then after we do a full, very, very thorough analysis of this collision, then we're going to hit a ton of ideas. All right, so the first thing is we want a before and after column. We're going to label everything. That helps with organization, and it helps a lot with recognizing our positive and negative signs. Okay, so typically the rule of thumb that I follow that you could follow too is that everything going to the right on my page is positive and everything going to the left is negative. But positive and negative just really mean opposite direction, but those are the directions that I choose. All right, so we know that momentum is conserved in both cases. So that means the mass times velocity of everything. So I'll do 2 times 2 plus 1 times negative 3. And that's going to give us 4 plus negative 3. And then we have 4 and negative 3, which sum up to 1 kilogram meter per second. So the total amount of momentum for the entire system, considering it's a closed system with no external forces, the total momentum is 1 kilogram meter per second, which means that after the collision, the total of the momenta for both of these two would equal 1 kilogram meter per second. So if we do 2 times 1, we got 2 kilogram meters per second plus 1, and I'll call it VF because it's a final velocity. And then if we subtract 2 from both sides, then we're going to get negative 1 equals 1 VF. So in the end, VF equals negative 1 meter per second. Okay, so that concludes our first question of how you solve for an unknown velocity. The second thing we're going to do is we know that momentum is conserved, but we don't know if energy is conserved. So what we want to do is we want to use the formula 1/2 mv squared, the one that we use for kinetic energy. So we already have all the values we need, but we're going to go ahead and do 1/2 mv squared for our first object before the collision, and then do the same thing for the 1 kilogram object before the collision, 1/2 v squared. Okay, and we're going to see if that equals the kinetic energy, the total kinetic energy on the other side. So we have 1/2 v squared plus 1/2, and then that's our new final velocity that we just figured out, mv squared. All right, so we can go ahead and do some quick math here. So we have 1/2 times 2 is 1, 2 times 2, or 2 squared is going to be 4. So we have 4 joules plus, and then negative 3 squared is 9. 9 times 1 is 9, and then 9 times 1/2 is 4.5. And then over here, 1 times 2 is 1, and then times 1 is still 1. And then finally, 1 squared is 1 times 1/2, which is 0.5. Okay, so now we know that these two clearly do not equal each other, that we have 4 plus 4.5, which is equal to 8.5 joules, which clearly does not equal 1 plus 0.5, 1.5 joules, which would mean that it's an inelastic collision, showing that the energy, the kinetic energy specifically, is not conserved. So that means some of the energy was lost through heat and sound. And now what we can do is look at it from a different perspective of looking at delta P, the change in momentum. Now, if we strictly take a look at the 2 kilogram object, which is this one over here, then we could do a mass of 2 and then look for its delta V. Our delta V is V final minus our V initial over here. So it's going to be 1 minus 2, and that's going to give us negative 2 kilogram meters per second for the impulse for our 2 kilogram ball. Now, taking a look at our 1 kilogram ball, if we do the same thing, it has a mass of 1. And then here is its VF, which is negative 1, minus its VI or V naught, which is negative 3. So negative 1 minus negative 3 is basically negative 1 plus 3. So that's positive 2. So the impulse of the second object is positive 2. So you would notice that they are the same number but different signs. And that is exactly what should happen if momentum is conserved. If one object loses 2 kilogram meters per second of momentum, then the other one should gain 2 kilogram meters per second of momentum. So the delta P for the 2 kilogram mass would equal the same thing as the other one, except different signs for the 1 kilogram mass. So that is another perspective you can take. You could use like this full drawn out version of the conservation of momentum with your pictures and arrows and negatives, which is the method that I like. For looking at the conservation of energy. This is the way to look at it, taking 1/2 mv squared of each of your values and then comparing them. And then finally, if you want to use impulse, you know that the impulses of each of them are going to be the same value, same magnitude, but different sign. And that can also be a way that you can find unknown variables or solve for different pieces of information. In this video, I'm going to be doing a simple harmonic motion overview for AP Physics 1, which will be good review for any high school physics class or any introductory college course as well. We're going to talk about what is simple harmonic motion, what are some main traits and ideas to know about it, and how do you solve for the period of a pendulum or a spring. The second thing we're going to take a look at is we're going to focus on a pendulum, and we're going to do a full energy analysis, take a look at the TME, the total mechanical energy, and then analyze where there are maximum and minimum values for restorative force, for velocity, energy, and all types of values associated with simple harmonic motion. And finally, we're going to be taking a look at a spring oscillating back and forth, and we will be looking at some more graphs with our position versus time, velocity versus time, and acceleration versus time, and you'll kind of be able to compare and contrast the spring versus the pendulum with these two different scenarios. So let's go ahead and take a look at simple harmonic motion and check out some of these main traits. So with simple harmonic motion, we're going to be taking a look at a pendulum and a mass attached to a spring. And with both of these, they have a restoring force or a restorative force, which is a force that pulls it back to its equilibrium position, pushes or pulls it back. So say, for example, for the pendulum, if you push it out this way or it just naturally swings out this way, a component of gravity is going to have a originally came from, and then same thing from the other side. Same idea with the spring. If you stretch it out this way and it has a certain positive displacement, then it's going to have a force in the negative direction, and that is its restorative force. And a rule about the restorative force is that it is proportional to the displacement. So the more you pull this pendulum outwards away from the equilibrium position, or the more that you pull or compress this spring in, the more restorative force you have pushing it back to its equilibrium position. That is a main trait of anything that shows a simple harmonic motion. Secondly, all of these things have a capital T, which is a period, the amount of time it takes the object to move back and forth. And with these periods, they are independent of the amplitude. So what I mean by that is if this object over here that's on the pendulum, if it swings back and forth in a really wide, full arcing motion, or if it swings back and forth in a short little arc, no matter how much you pull that pendulum back and let it go, its period of how much time it takes to swing back and forth is actually going to remain constant. And the reason why that would remain constant, and just to put it simply, if you take a look at this orange arc over here, the arc length of that path right there is a fairly small distance. So when you have a smaller distance, you will also have a smaller average velocity, because if you pull it back, the component of gravity that's going to accelerate it isn't going to be quite as big as that green arc. And then for your green arc, when you pull it back, it has a greater distance to travel through, but it has a greater average velocity. Okay. In the end, the period is going to be exactly the same. Same thing for the spring. If you pull it a short distance away and then let it oscillate back and forth, it's going to move a little bit more slowly on average, but it's not going to be moving very much distance. And if you pull it out really, really far, it is going to release and then oscillate back and forth much faster across a greater distance. And in the end, the period stays constant. Third of all, we have a bunch of sine and cosine curves that are naturally produced when you take a look at the motion of these objects, whether you're taking a look at the energy, the position, the velocity, and so on. You're going to have all kinds of sine and cosine curves. Now, when taking a look at the period for both of these, the pendulum has its own formula. We'll call it T sub P, and that is 2 pi the square root of L over G is the length of the string, and technically that is the length from the center of mass all the way up to the very top of the string. That would be your L in meters. And your G value, you can go ahead and assume that is 9.8, unless you're on another mass other than Earth, which maybe you're on Jupiter or the moon. In that case, you might have a different G value. Other than that, you can assume that it's going to be 9.8 in most cases. And then for the spring, it has a different formula because it doesn't have the same properties as a pendulum. With this, we'll call it T sub S, and that formula is 2 pi the square root of m over k. M is the mass of the oscillating object connected to the spring, and then k is the spring constant measured in newtons per meter, which is basically how stiff or stretchy the spring is, how much force is required to stretch or compress it 1 meter. So using either one of those formulas, you can go ahead and find the period, the amount of time it takes to complete one full cycle for each of those oscillating systems. So now let's go ahead and focus on the pendulum and take a look at an energy versus time graph after we talk about some important values. So let's say, for example, we pull the pendulum back to position A. This is its maximum displacement from its equilibrium position, its equilibrium position being B over here. So we'll call this EQ for equilibrium position. And then this is when it's pulled back in the negative x direction, and this is the positive x direction. So A and X, or excuse me, A and C are where it's at its maximum displacement, or where it's showing the amplitude of the pendulum. Now at these points, the velocity is going to equal 0 meters per second. So when something swings as far as it possibly can, it's going to hit an instantaneous velocity of 0. Secondly, this is where you have the maximum amount of restorative force. We'll just call this force, and then I'll put RES as a subscript, and the maximum amount of acceleration as well, because force is directly proportional to acceleration. As I said before, there's a component of gravity that is going to pull the pendulum backwards towards its equilibrium position. So let's take a look at what that looks like real quick. So we have FG over here, which is parallel to the string. So that's not going to cause it to have any motion swinging back and forth. It's only a component that is perpendicular to the string. Now when it's up here, we have FG pulling it straight down as usual from the Earth, but then we have two different components. We have a y component and an x component. And this x component over there, which would be Fg sine of theta, would be the perpendicular force that pulls it back to its equilibrium position. Okay, so same thing on the other side, except that perpendicular force is going to be pulling back in this direction. At the middle position, we do not have any restorative force, but we do have a special value here. This is where we have our maximum velocity. The reason why we have our maximum velocity is this. The way I like to look at it is if you're taking a look at this full arc from A to C, gravity as some component that is pulling it downwards over here, and it's letting it speed up for the whole first half of the swing, and the second half of the swing where it's moving away from the earth, it's going to be slowed down. So it's speeding up the entire time from A to B. Therefore, B is going to be its maximum velocity, and then it's going to slow down from B to C and then hit a velocity of 0 at the other end, because that's where it reaches its maximum displacement or amplitude. And again, that's where you have the maximum amount of restorative force and acceleration as well. All right, so let's go ahead and get into the energy versus time graph, and let's take a look at what the kinetic energy looks like first. So the reason it looks like that is if we start from position A and release it from position A, it has no velocity at first. So if we are taking a look at the kinetic energy, which is 1/2 mv squared. If the velocity is always squared, the energy is always going to be positive, so we're definitely not going to dip below the x-axis. So first of all, it's going to start at a velocity of 0 because of the 0 meters per second, its resting position as it's released. And as it's released, it has the most amount of force in the beginning, so it's going to have the most amount of acceleration at the beginning, so that velocity is going to rise quickly and then less and less until it reaches its maximum velocity at this equilibrium position right over here. And then this is going to be position A, where it is the negative x position. And then as it rises up towards C, it's going to feel more and more of that restorative force, which is going to cause it to slow down and reach 0 once again. This is position C, where it's at its positive x position. And then that restorative force is going to slow it down, make it go to 0, and then it's going to send it back the other direction. And then remember, it's not going to dip below 0 because it's v squared. So it's going to cause it to speed up and reach its maximum kinetic energy and its maximum velocity back to its equilibrium position again. And then as it rises up or continues to rise up towards position A, it's going to slow down, and it's going to slow down at an increasing rate. So if it's slowing down more and more, it's going to go towards 0 faster and faster, and then it's going to hit position A once again at its negative x position. Now that would be considered one full period because we started at A, which is the negative x position, all the way back to A, its negative x position once again. Now for the gravitational potential energy, which is mgh, that's largely just going to be determined by the h value, which is the height. This would probably be our baseline height. Let's go ahead and make this a different color. This is probably going to be our baseline height right over here. At the very bottom of our swing, we'll call that 0 meters. And this one is actually going to end up mirroring this graph over here. And at the beginning, where it starts at position A, is where it has its maximum height. And then its height is going to drop quickly because it has that large restorative force in the beginning. So it's going to start from position A, the negative x position, and then move towards a height of 0, where it reaches its equilibrium position. And then the rate at which it's increasing its height is starting to increase in the beginning, and then the rate that it gains height is going to decrease towards the end because that restorative force is pushing back on it, and then it's going to reach point C, its positive x position. And then that restorative force is going to make it lose its height fairly quickly in the beginning and a little bit less at the end when it reaches back to its equilibrium position. And then it's going to finally swing back up to its final position, position A, its negative x position. And it should always basically like mirror or be symmetrical to this invisible horizontal line right here, because kinetic energy and gravitational potential energy transfer to one another and have an inverse relationship. And then if you want to take a look at their total mechanical energy would be a line that looks something like this. And that orange line would be your TME, your total mechanical energy, which is the sum of these two. And that is going to stay constant because the energy is conserved in a closed system. The energy is just being converted back and forth from kinetic to gravitational and vice versa. Now, going to our final scenario, we're going to take a look at a block oscillating back and forth as it's connected to a spring. And that force, that restorative force that it feels, can be represented by Hooke's law, F equals negative kx. And that negative is because it is a restorative force. So let's say, for example, our scenario is that it's moving through its equilibrium position right there, and then it's going to move to the maximum amplitude that we'll call positive x, and then it's going to reach a velocity of 0 at its maximum displacement. That's where it's going to reach its maximum restorative force and acceleration as well. And then same goes for its greatest negative displacement as well. It has a velocity of 0 and it has a maximum restorative force just pointing towards the other direction, towards the right, because it's compressing the spring. So the spring is going to push to the right. So that's where it's going to have the maximum restorative force and acceleration as well, just in the other direction. All right, so let's go ahead and take a look at these graphs. So if you're thinking about what's happening with the position versus time graph, I think about it in terms of slowing down and speeding up, and also in which direction. So we're going to call this direction positive, and then this direction negative. So from the equilibrium position to its maximum positive displacement, it's going in the positive direction, but it's slowing down. So we're going to rise in the graph, and we're going to make our slope progressively more flat. And then that is going to be our positive x value from its equilibrium position. And then as it gets pulled backwards, remember it has its maximum amount of force over here. So it is going to move back steeply towards the other direction. And then as it does that, it's going to hit position 0 right over here as it moves through the equilibrium position. So it's going to move in the positive direction and slow down, and then it's going to speed up in the negative direction and then hit 0. This is where it's at its equilibrium position one more time. And then now it's starting to compress the spring. So it's going to slow it down in the negative direction. So we're going to go underneath 0, but we're going to make sure that slope becomes more and more flat. And then as that restorative force over here pushes back in this direction, because the spring is compressed, it's going to give it the maximum amount of restorative force, and it's going to cause it to speed up towards that equilibrium position. So from that negative x position, it's going to push it back to its equilibrium position. And then we're going to get a nice little sine curve there. And then when you go to your next graph, you can do that a couple ways. We know that the slope of our position time graph is basically delta x over t, which is the velocity. So you can produce your velocity graph one of two ways. You can basically think through what's happening to the velocity through the equilibrium point at our positive x position, our negative x position, etc. Or you can take a look at the slopes of your position versus time graph. Okay, so whichever one is your strength, I would definitely go there. So for the position versus time graph, we have slopes that are going in the positive direction, but it's positive and becoming increasingly more flat, and then it's hitting a instantaneous velocity of 0. So it's going to look something like this in the beginning, and here's our instantaneous velocity of 0 at this positive x position when it's coming from the equilibrium position. All right, so here's where it's at its maximum stretch. And then from here to here, now it's dropping down in the negative direction, and it is becoming greater and greater in the negative direction until it reaches its maximum velocity, maximum negative velocity at the equilibrium position right over here. Okay, as it sweeps through its equilibrium position, it is going to move closer to zero, which means that it is slowing down because now it's going through its equilibrium position and starting to compress the spring. So the spring is fighting against it to make that velocity that is a large negative velocity move towards zero, which means it is slowing down. And then at its greatest restorative force, it's going to push it up with a fairly steep slope. And then that's going to start to flatten out a little bit towards the end. So this is where it has its greatest negative displacement before the spring pushes it back towards its equilibrium position. And then finally, we're going to take a look at the acceleration graph. And that you can also do one of two ways. You can take a look at the slopes of your velocity graph. So we know the change in v per time is the acceleration, or again, you can kind of think of all the conceptual ideas of the restorative force and acceleration as the spring is oscillating back and forth. So the way I look at it is thinking about what's happening with the force. Remember, the force and the acceleration are directly related to one another. So whatever the force is doing, the acceleration is also doing as well. So the first thing the acceleration is going to do is it's going to start at its equilibrium position and temporarily not have any acceleration at its equilibrium position because the spring is neither stretched or compressed at that point. And then as soon as it passes the 0 point going towards the positive direction, it's starting to stretch the spring, and the spring is going to pull it back towards its negative direction. So it's going to have more and more negative force until that force is going to max out at the positive x position. So remember, once the spring is pulled all the way to its farthest point, that's where it's going to have its maximum restorative force. That's this maximum negative acceleration because it has a maximum negative force. And then it's going to pull it back to zero. So it's going to have less and less negative force until it reaches that equilibrium position. And then now it's starting to compress the spring. So the spring is going to fight back against it and push to the right. So now we're going to go into the positive region. And then we're going to have more and more positive force until it reaches its maximum positive force at its greatest negative displacement because it's compressed as much as possible. So it's pushing back a lot. And then as it pushes it back to its equilibrium position, it's not going to be pushing quite as much until it pushes not at all at its equilibrium position to end off. Okay, so again, I like to think about it in terms of force because force is directly proportional to acceleration. So for me, conceptually, that kind of makes a little bit more sense. And now we have completed our acceleration versus time graph and completed one full period for the position versus time graph, velocity versus time graph, and acceleration versus time graph. So to sum things up, when you're analyzing things in simple harmonic motion, you're basically taking a look at different energies, positions, velocities, and accelerations, producing all kinds of different sine and cosine curves based on how the values change. You just have to be aware of how the restorative force and acceleration are working and where there are minimum and maximum values. A rotational motion and torque overview for AP Physics 1, which will be a good review for any high school physics class or introductory college courses as well. First, we're going to take a look at translational versus angular variables. So at this point, you want to make sure you have a good foundation of kinematics and forces, along with momentum and energy, to make sure that you can fully understand angular motion. So everything that you've learned up to this point has mostly been translational motion, but now we are changing it and taking a look at angular variables, equations, and concepts. Secondly, we're going to be taking a look at torque, different concept scenarios and formulas that cause angular acceleration. And then third, we are going to take a look at the moment of inertia, so rotational inertia, and how it pertains to angular momentum and how mass is distributed for an object. And then finally, taking a look at rotational energy and all different concepts associated with that and with rolling objects. So let's go ahead and get started taking a look at translational versus angular variables. So let's take a look at this table with translational and angular values. So translational values are the ones that we're a little bit more accustomed to. It is when all the particles of a certain mass are all moving uniformly in the same direction. So basically something actually moving across a room, moving down a street. We have delta S, which is basically like the delta X. A delta S would just be like moving in a specific arc. That is in meters as usual for any kind of distance or displacement. And the velocity is how many meters you're moving per second. Acceleration is the rate at which your velocity is changing, which is meters per second, shown as meters per second squared typically. Time is in seconds, showing the amount of seconds that has elapsed. Force is the amount of push or pull measured in newtons. And then we have a mass that is in kilograms as our standard unit. Now we're taking a look at angular values. Now we're concerned with variables that are very similar, but definitely a little bit different. So now when we're talking about angular motion and we're talking about rotation, we're more focused on the actual thing itself rotating. So if something is rotating, that means it has an internal axis. That basically means the thing itself is spinning. So kind of like an Earth day, as opposed to something like an Earth year where the actual thing is spinning itself and has an internal axis. So we have a delta theta, and oftentimes people are a little bit more familiar with degrees, and theta is um, also expressed in radians as well, which you may or may not be as familiar with. And a radian is the ratio between the s and the r, the arc length and the radius, as shown in the picture over here. So we have a delta theta, which is in radians. We have an omega now. So instead of meters per second of how many meters you're traveling across a certain space per second, it's how many radians you are rotating per second. The alpha is how many radians per second you're gaining or losing per second, which is radians per second squared. We have time, which is just time as usual. And then we have torque. And then torque is typically in a Newton meter. So a torque is basically any force that causes a rotation. So these forces mostly cause linear motion, like sliding something across a room. This torque might just be spinning a wheel or an actual person rotating. And then instead of the inertia from an object just having a certain amount of matter, it is based on its moment of inertia or rotational inertia, which is in kilograms times meters squared. Here's a few other formulas. Those are not on the AP1 formula sheet, but things that you may use. You can get theta, omega, or alpha by taking any of those linear values and dividing it by r. That might be something to just keep in mind or keep in your notes moving forward. Now, what you can do is you can use all the same formulas that you're using before, but it's just replaced with the new values for angular motion. For example, we have our theta equals theta naught, our initial displacement, plus omega naught times t plus 1/2 alpha t squared. So that is typically the most common formula you may use. The second one is going to be omega equals omega naught plus alpha t. Now, there is a third kinematics formula that is fairly popular, which is the v squared equals v naught squared plus 2a delta x1. That one is not on the AP1 formula sheet. You could also use that if necessary, which the version of that in rotational motion would look like this. Where instead of taking the linear values that typically look like this, we were replacing it with all of the rotational values. So as you're solving these angular problems, it's basically going to be the same sort of kinematics you've been solving for with translational motion. You just have to change your perspective or lens at which you are viewing these problems in terms of radians. So how much of the circle are you sweeping through? One complete circle equals 2 pi radians. So if you have something that says 5 rotations or 5 revolutions, you can go ahead and take 5 times 2 pi, and that'll give you your delta theta. And then as far as your omega goes, you're looking at it in terms of how fast it's rotating through the circle per second. This is the rate at which you are gaining that omega, and then time is the same. And then we'll get into torque and moment of inertia a little bit later into this video. Now let's move on to discussing torque. Torque is any force applied a certain distance from the axis that causes a rotation. So our first example we're going to take a look at is this wrench over here. And if you apply any type of push or pull to this handle in a certain way, it'll cause it to rotate, hence causing it to be a torque. So torque in this sense is going to be force times R, which is the lever arm, times the sine of theta. Now, when you're taking a look at it, we have a certain force being applied. We'll go ahead and call that FA for that applied force. And one rule about torque is that the force that is parallel to the lever arm doesn't cause any torque. So if you had any kind of force pulling or pushing left or right on that handle, it's not going to cause any rotation at all. Now, the portion of the force that causes the rotation is the part that is perpendicular to the handle. So if we take this angled force and this 25 degrees, that's 25 degrees from the horizontal, we can make a triangle with an x component and with a y component. And the y component is the only component that actually causes the rotation. So what you would do is you would plug in the FA, this applied force over here, whatever number that may be, times the R, which is the lever arm. The lever arm is the distance from the axis of rotation, which would be from here to about here, whatever that distance may be, and then times the sine of theta, which is basically going to give you this orange portion over here once you multiply it by the sine of that 25 degrees. The way I think about it is that sine of 25 degrees is almost going to give you like a percentage of that force that acts perpendicular to that wrench handle that causes a certain rotation. If it's pulled perpendicular to the axis straight up and down, then it's going to be sine of 90 degrees, which is 1, which gives you 100% of that force is going into rotating that object. So once you take that applied force, that lever arm, and that sine of 25 degrees, that's basically giving you the torque caused from this orange vector over here. But you don't necessarily need to find that component of the triangle on its own. The sine of 25 degrees is going to go ahead and take care of that for you. Okay, going on to our second scenario. We have two objects that are balancing and causing a net torque of 0 Newton meters, which is a common scenario to look at. And we know that the net torque is 0 because of the plank being completely balanced. We have a certain force of gravity, which we'll maybe call, we'll call this one M2G, and then we'll call this one M1G. And those two forces are causing a torque. Now, if you take a look at the scenario, it doesn't look like you're rotating it because a wrench, you like actually physically see it turn. But since this one is static, we have two things that are causing a torque that are canceling each other out. So this force over here is attempting to rotate this plank clockwise. And this force over here is causing a torque, causing it to rotate counterclockwise. And then those two forces would be canceling each other out. So we know that 1G times that lever arm. So maybe we'll call this lever arm R1, and then maybe we'll call this lever arm R2, minus our M2G times R2 would equal 0. Which basically means that these two are equivalent to each other once you add this one to the other side. Now, the only other thing to consider would be this, if the actual plank itself has a significant mass. Now, if the plank itself has a significant mass, which all you would do is this, you would take a look at the amount of the plank that is on one side, and then you would find the center of mass of that section, and then it would have its own little mg causing torque on that side. And then same thing with this side. You find the center of mass of this part, and it would have its own little mg. Okay, for example, if the entire plank was 4 kilograms, then this would be 2 times 9.8, and this would be 2 times 9.8 as well. And each of those would have their own little lever arm. As I said, that would be the midpoint of this half of the plank, and then the midpoint of this half of the plank. It isn't always centered. It could be sitting, a third of the way from the center. The plank could really be placed anywhere. So you just have to find the center of mass, or the geometric center of that portion that is on that side of the axis. Okay, now taking a look at our next one is taking a look at a pulley system over here. So these ones can get pretty complicated. The main idea is this, that we have a force of tension pulling this part down, and we have a force of tension being applied this way as well. So this would be something like a T1 and a T2. We could tell that based on the mass that's hanging on this end is that this T2 is going to be a little bit greater. So let's go ahead and make this vector look a little bit greater. And what you would do is you would still subtract the two to get the net torque, except the net torque isn't going to be 0. So what it would look like is this. We know that this is going to be a little bit larger than the torque caused by T1. So let's go ahead and say T2 times R, which is the radius of the pulley, minus T1 times that same radius of the pulley, equals our net torque. And then our net torque is going to be I alpha, which is basically Newton's second law, which is ma. And then the equivalent for angular motion is going to be the moment of inertia, or rotational inertia of the disk, times alpha, how many radians per second squared that the system is accelerating. All right, lastly, let's go ahead and take a look at this ladder or plank leaning against a wall. And we're going to go ahead and analyze the final torque formula, which is torque equals the perpendicular radius times the force. And basically what that looks like is something like this. Say, for example, you have a bucket hanging on a ladder or a plank over here. What happens is it has a certain force of gravity pulling it down, which is mg as usual. And then the radius perpendicular to it is going to be this one right here. In orange, this distance from here to here. That is your lever arm or radius that is perpendicular from this pivot point over here. Because remember, this ladder or plank over here is attempting to pivot or rotate, but it's bumping into this wall over here, which is also causing a counter torque. But if you were taking a look at this formula right here, this is another option of something you can use. You don't necessarily have to, but something you could utilize of using a force that is applying some kind of torque, and then using that radius that is perpendicular, the axis of rotation being right over here. Now, one last idea I'm going to point out on the screen is taking a look at these different objects. And these different objects over here have their mass distributed in different ways. The farther the mass is from the axis of rotation, the more rotational inertia you have. So these are a bunch of formulas, none of which are on the AP Physics 1 formula sheet. So if you need one of those, it'll probably be provided within the question. But the main idea is knowing that the more mass that's away from the axis of rotation, the more rotational inertia or resistance it will have to rotating. For example, this hoop over here that has an axis that's right through the middle of it, all of its mass is distributed as far as it possibly can. So it has a coefficient, an invisible coefficient over here of 1, which means it has the maximum amount of rotational inertia, as opposed to something like this disc or cylinder that has half of the amount because the mass is distributed a little bit more evenly. So the rule is basically that if you have more mass towards the center, something is going to have less rotational inertia, thus in most cases is going to rotate a little bit more quickly and easily. Okay, so with that idea in mind, let's go ahead and slide over to the next topic, which is angular momentum. Now, for our final couple of topics, we're going to be taking a look at angular momentum, and we're going to be taking a look at rotational kinetic energy as well. And we are going to tie in the moment of inertia into both of those ideas. So in this picture over here, we have a figure skater that is rotating. And as they're spinning, one would analyze the formula L equals I omega, where L is going to be the angular momentum. The I is going to be the rotational inertia or moment of inertia, either one. And the omega is going to be that angular velocity. Now, when you're taking a look at these values, basically how it works is that the angular momentum is conserved as long as there is no external forces. So if the system is basically just the person over here and they are spinning on a frictionless surface over here, then we're going to say the angular momentum is conserved, which means that would be the product of your I and omega would be the same exact number. So what happens is if you increase the rotational inertia, then you would decrease the angular velocity, and vice versa. If you were able to decrease that moment of inertia, then your omega value would increase. Now, how do you do that while you're spinning? That's all based on the distribution of mass. So, as we were talking about before, those different shapes, as your mass moves farther and farther from the axis of rotation, the axis of rotation would be right over here through the person's body. If you take your arms and legs and you put them outward, then you are increasing the rotational inertia. So the way you do this is you move your mass farther from the axis. So that's the axis of rotation. Okay, and then vice versa over here. If you take your arms and then you tuck them in and you bring your leg and you bring it inward and you bring that mass towards the center, you still have the same amount of mass, but the way in which it's distributed is different. So if you bring that mass closer to this red dotted line, then your rotational inertia decreases, hence causing your angular velocity to increase. So the amount of radians that you would go around per second would increase and you would see the person spin much faster. Now, that same thing applies to people and things. One of the classic cases would be taking a look at an object that is rolling down a ramp. So we might have an object up here, and as it's rolling down the ramp, we have a couple of different things going on with it. So let's go ahead and take that object and pull it out over here. And here's the surface right underneath it. And if we were to draw the forces acting on it, we would have mg as usual, the force of gravity. We would have a normal force perpendicular to the surface, and then we'd also have the force of static friction. Okay, the reason why it's static friction is because the ball itself, if it's rolling and it's not slipping, slipping would be kinetic friction because it'd be the same area or part of that object that is going against the surface itself, but it's just each part of the ball or disc that is touching that surface and then getting pushed back as it's trying to slide, and that causes it to rotate. Now, that FFS actually causes its rotation. So there is a certain radius for this object, so we'll just call it a disk. And if you were to find the torque of that force of static friction, you would get your force of static friction by possibly doing the coefficient of static friction times the normal force, and then times r, the radius, which would be the actual radius of the disk itself. Now, as that thing is rolling, it is going to have a few different types of energy. Now, if you're using the conservation of energy, then the initial energy equals the final energy, and that's in the instance that there is no work being added or subtracted to the system. So in this case, we are not taking a look at any work being added or subtracted to the system. So we're saying all the initial energies sum up to the final energies. Now, because the object is off the ground, it definitely has some gravitational potential energy. And if it remains at rest in the very beginning, then it doesn't have anything else. But then afterwards, it's definitely moving. Now, it's moving in two different ways. It has a KT, translational kinetic energy, and has a KR, its rotational kinetic energy, because it is actually moving across this distance, which is the KT, the translational or linear type motion that it has, and it has KR, which means the object itself is being rotated. So if you were to take a look at these different things, we have KT, which is 1/2 mv squared. We have KR, which is 1/2 I omega squared. And then we have gravitational potential energy, which is mgh. Now, if you're comparing different things that roll down the ramp, what it would look like is this. Now, one of the classic cases to be looking at would be a ring versus a disk. So our ring has all of its mass distributed as far from the axis of rotation as possible, and the disk has all that mass evenly distributed. The I formula for each one of them would be this. For the ring, it would just be mass times radius squared. For this one, it would be 1/2 times the mass times the radius squared. So the ring has a lot more rotational inertia. So if you want to see which one would win the race going down the ramp, assuming that they're the same mass and same radius, all you'd have to do is analyze it like this. If you have the UG, and then if we subtract the KR from both sides, then that would equal the KT, the translational kinetic energy. Now, the translational kinetic energy is going to be the thing that tells us which gets to the bottom first and which one is traveling more quickly at the bottom. Now, the way I'd look at it is, now that we have our gravitational potential energy, that's going to be the same for the ring and the disk because they have the same mass, they have the same value of G, 9.8, and they start from the same height. So this is going to be the same for the ring and the disk. And then for the KR, the rotational kinetic energy, the way I would look at it would be like this, is that because the ring has a lot more of its mass distributed away from the axis, the force of static friction is going to have a much harder time rotating it around. So it's going to make that rotational kinetic energy go up and then therefore cause the kinetic energy, the translational kinetic energy, to go down once you subtract this larger number here. And then that would mean that the ring has a lower translational kinetic energy, which means it has a lower velocity. Now, to work out that entire problem is a pretty lengthy process with a lot of substitutions. If you would like to see how that's worked out, you can go ahead and click on the link above and then see how all those numbers are substituted out and then solve for it to find that exact velocity. So that pretty much sums things up. We went over all the different angular variables, taking a look at all the situations with torque, talking about rotational inertia, angular acceleration, angular momentum, and lastly, rotational kinetic energy. So I hope that was helpful to you. Thank you for watching and listening.